Okay, so let me just begin the streaming and we can begin. But we have to start now, so no, we will use this. So the coffee break, we'll try to sort it out, okay?
Okay, I'll speak to you.
All right. Let me just put it on the big screen. Okay, hello everyone. It's a bit unusual today because we're in a cinema, but we begin with a movie from famous Wyn Evans from Cambridge. Wyn, the screen is yours.
Thank you, Lukasz. I hope the hearing is okay and you can hear the talk. If not, do interrupt. So I was at the meeting earlier this week, but I've had to come back because lectures start today, and I have to rush off at the end of this to give my first lecture. So it may be that there's not enough time to answer all the questions, and if so, but please just send the questions in the Slack channel if you have any, and I'll try and answer them. So I'm going to talk about work that was largely done by Zofia Kaczmarek, who I think will be well known to some of you, Peter McGill, and Lee Smith. So we heard a very nice review on the achievements of the OGLE program, and so optical microlensing surveys towards the bulge have been conducted for a number of decades now and have substantial scientific achievements. It's also possible to do microlensing searches towards the inner galaxy in the infrared, in the K-band, and that was first suggested by Andy Gould in 1995. And the VVV survey is one survey that allows us to do that. It was a survey of the southern galactic disk and bulge carried out with the VISTA telescope across 2010 to 2019. And it was primarily interested in all manner of variable phenomena. So it wasn't particularly tuned for microlensing. It was also interested in examining the variable star populations in the inner galactic disk and bulge. So there are differences between OGLE and VVV. OGLE is much larger. It covers over 3,000 square degrees in the sky, and it monitors regularly over 1 billion sources. And the photometry spans the range down to the 21st magnitude in I. It also has some very precise magnitude accuracy at the bright end, and the cadence of observations can be very high in the inner galactic bulge. The VVV survey is smaller. I'll show the footprint in a minute, but it's confined primarily to the inner bulge and disk, and it isn't as deep in K as the OGLE survey is in I, and the cadence of the observations varies, but it is of the order of days. And of course, the principal advantage of the VVV is that it is an infrared survey, so it is able to pierce some of the most dusty areas in the center of the galaxy. And so this shows the VVV footprint in yellow as compared to the much larger OGLE footprint in the background. And so the VVV is primarily concentrated on the inner bulge, centered around the galactic center, but there is a strip along the galactic plane. The data set is of the order of 700 million VVV light curves, and we know roughly the optical depth of microlensing is of the order of 1 in a million, so we can expect of the order of thousands of events. But first, we have to find the events in an efficient and automatic way among the light curve catalog. And this we did somewhat earlier using machine learning I just need to briefly explain this, but it's not the main focus of the talk. So, as always, you can train a classifier. You need to extract some features from the light curve, and then you need to give the classifier examples of microlensing and contaminants. One of the principal contaminants is cataclysmic variable stars. And so the four features that we extracted are shown here. They're basically the standard deviation of the residuals for data points within 2 times the Einstein crossing time, and exterior, that gives the first 2. And then there is the von Neumann ratio eta, and the difference between the likelihood of the point source point lens model and a standard constant baseline model can give us something like the delta Ihanec information criteria. And you can see here how in projections in 1 dimensions, the various distributions can be separated. And so the idea is to design a classifier, train it, and then apply it to the VVV survey. So the classifier achieves 97% accuracy in identifying simulated microlensing events in the validation set. We ran the classifier over the VVV data set, and that produced a catalog of the order of just under 2,000 microlensing events. And for these events, we used a Bayesian analysis because the likelihood surface is quite complicated to provide distributions of the microlensing parameters, including the Einstein radius crossing time. And you can see some examples of the data and the fitted microlensing light curves here. So these were found automatically. Some of them are clearly very convincing, but some of them, the data coverage is partial, so the microlensing parameters have some considerable uncertainty. We can also compute the efficiency as a function of spatial coordinates and timescales for various. So we're looking here at 5 plots showing 5 different values of the Einstein crossing time, and the color shows us the efficiency. So there is a high cadence region that you can see clearly where the efficiency is much higher in all the plots. And if you look carefully on the plots, you can see little dots, and those are the locations of the found microlensing events. So now what we want to do is try and understand whether the results of this survey are in good accord with theoretical predictions. And our job here was made a lot easier by David Specht and Eamon Kerrans, who have produced this very nice online simulator. It's perhaps not a brilliant name. They call it Marbles. So that's the Manchester Besançon microlensing simulator. It uses the Besançon model of the galaxy, and you can vary things like the cadence of signal to noise and the field of view that you wish to examine. So it's a fun tool to play with. They claim that it is a good reproduction of microlensing parameters towards the center of the galaxy, and we can now put that claim to the test. So now we're looking at the VVV footprint. That's the leftmost panel in galactic longitude and latitude. And this is a Marbles map. It's been split up into white fields. Those are the dotted white lines. And those correspond to fields in the VVV footprint. So we'll be able to directly compare predictions in those white bins from the model and the data. And what also is shown in the color is the mean Einstein crossing time, so that you can see that there are definite gradients that we would hope to be able to distinguish in the Einstein crossing time as a function of galactic longitude and latitude. So, for example, you can see the bright yellow portions of the longest mean Einstein crossing time are at a galactic latitude of 0 and at the extremes of galactic longitude. And the other two plots show the varying efficiency in recovering microlensing events for a short timescale event, 9 days, and for a very long timescale event. Because obviously to try to estimate any spatial gradients in the data, we will have to take particular care to understand the spatial gradients in the efficiency, which will influence our data results. So again, we see the split up of the inner bulge in galactic latitude and longitude into these bins in the left, and then on the right, it's a short table showing the 12 bins and then giving the number of VVV events in each of these bins. So for each of these events, we have distributions posterior to the microlensing parameters. So as I mentioned, we need to take particular care in estimating the efficiency in recovering microlensing events as a function of timescale under the particular VVC observing pattern. And here you can see stacked plots of efficiency versus timescale for various colors of bins. So you can see bins, for example, at a relatively high latitude, a modulus of B greater than 1 degree in green, and then you can see bins corresponding to negative latitudes and positive latitudes in red and blue. And so there's, as I mentioned, a small window of high cadence data around a longitude of 5 degrees and a latitude of about 2.5. And you can see that pattern in these plots. And you can also see two vertical lines that have been drawn, and that is where the efficiency is very low. Obviously, our results are going to have to be corrected by this efficiency. And when the efficiency is very low, we're going to mask the data. And so we're only going to use the unmasked portions between the dashed gray lines. So this is now a rather busy plot. So we're just looking at 4 bins now, and the first thing to focus is on the purple lines. So these are the efficiency corrected values of the bin heights from the VVV events obtained using hierarchical inference. And so the error bars indicate 68% confidence levels. And you can already see in the shaded purple regions, the vertically shaded purple regions, that the errors have become very big because, of course, the efficiency is very low. And so those parts of the data have been masked, and we will only use the parts of the data that lie in the white or unmasked portions of these plots. We can do the same for the simulator, the marbles simulator, and those are shown in blue. So their bin heights as predicted using the marbles 2 simulator. And then for each of these distributions, we follow a trick pioneered by Lukács, and we fit log normal distributions to the data points using hierarchical inference, only including the data points within the mask. And so those are shown as dashed lines. The vertical lines are perhaps not so important to worry about for the purposes of this talk, but they show medians and confidence intervals for the means of the log normal distributions fitted to each histogram. So now we're in a position to compare, what we're now going to do is use the peak timescale. We're in a position to compare the data and the marble simulator. So the marble simulator is now shown in top left, and the inference on the peak timescale is shown on top right. And color gives us the timescale in days. So there's already, you can see, rough agreement in peak timescale. If you look at the two plots below, you see the difference between the model and the data, and then the confidence interval for determining the peak timescale from the hierarchical inference results. And you can already see that the visual impression is correct, that the Marble simulator does a good job of predicting the peak timescale distribution, certainly within about 1 sigma, almost across the entire field of view of the VVV survey. So that's a very reassuring result, certainly for Eamon Kerins and David Specht. Quite a lot of assumptions go into simulating distributions of microlensing events with regard to the galaxy, because of course you have to simulate distributions of deflectors, distributions of sources, and their proper motions. And so the center of the galaxy is also structurally quite complicated with a galactic bar, but it looks as though the Marbles simulator is really performing very well compared to the data that we have from the VVV survey. And I think that's similar to what was found with Ogle 4. I believe it also does a good job after refinement in reproducing the Ogle 4 results. So now we're just going to look at some timescale trends as a function of galactic longitude and galactic latitude. So again, the plots are rather busy, but perhaps the important ones to focus on are the purple lines and the blue lines in the upper two plots. So the purple lines are the inference from the data, and the blue lines are the Marble prediction. And you can see they are, of course, coming with error bars, but you can see that the trend in longitude is really rather well reproduced as we move from positive longitudes through 0 longitude to negative longitudes. The purple and the blue curves in the upper left panel have a very similar form and are certainly consistent within the errors. That's not really the case for the left plot, which shows the same thing as a function of latitude. Of course, the errors are large, so probably the results are still statistically consistent, but it's certainly true that the trend of timescales increasing with decreasing latitude, which is predicted, is the reverse of what is actually seen. Although, again, I think it's probably fair to say that given the cadence of the VVV survey, it's probably premature to conclude that there is a real conflict here. So that raises the question, as we know that more powerful surveys in the infrared are due to come online, in particular the Nancy Grace Roman Space Telescope, which is expected to be launched in 2027 and has a wide field instrument which will observe in the near infrared, similar to VVV's short K-band. It raises the question, where would we like to look to try and pin down the gradients that we see, in this case, in the timescale distribution? So we can use Marbles to provide timescale distribution predictions for all our spatial bins. And here they've been colored red if they're in central longitudes, that is a modulus of the longitude less than 5 degrees, and blue if they are in non-central longitudes. And you can see a distinct difference in the predictions, which we would hope to be able to pick up with something like the Roman Space Telescope. So I'm going to return to that in a moment or two. Let me just begin my conclusions. So we've used near-infrared photometry and astrometry from the VVV survey to analyze the microlensing events. we looked for a parallax signal, but we also fitted standard point source, point lens light curves to each event. And the fitting is done using nested sampling to characterize the multimodal and degenerate posterior distributions. So that was the starting point for this work. We then used those data sets to try and understand spatial variations in the inner galaxy. So we were interested in the spatially resolved peaks and means of the timescale distributions. And we also looked at the marginal distributions in strips of longitude and latitude. And in particular, we were interested in understanding whether they were in good accord with theoretical predictions, particularly from the Marble simulator, which is, of course, based partly on the Besançon model of the galaxy. And there, I think the results are very positive. The results agree at a 1 sigma level with predictions based on the Besançon model. And so that gives us a lot of reassurance that the Marble simulator is actually really quite a powerful tool for investigating microlensing towards the center of our galaxy, and in particular comparing the results of surveys such as OGLE and VVV with theoretical models. So I was very impressed with that result. It gives a lot of confidence to using the Marble simulator. In the data, we did find that event timescales in the central bulge fields are on average shorter than the non-central fields, and this is indeed predicted by the Marble's models. Our data were not sufficiently densely sampled in cadence to pick up the signal of the galactic bar. So we know the near side of the galactic bar is at positive longitudes, and so we should expect on average shorter timescale events at positive longitudes than negative longitudes. But the sampling in VVV was insufficient for us to be able to pick up that signal of the galactic bar. So our ability to probe the structure of the bar or the bulge with this near infrared sample of microlensing events is limited by the survey's sparse cadence and the relatively small number of detected microlensing events, compared, of course, to dedicated optical surveys such as OGLE, which have many more events. But as I alluded to, there is the possibility of carrying out microlensing searches in the infrared with the Roman Space Telescope. So we can use the Marble's maps, of which we now have quite a lot of confidence, to try and figure out where we would place fields to be able to maximize any asymmetry and therefore detect possible signatures of the galactic bar, for example. So we can construct these maps directly from the Marble simulator by taking, for example, the peak timescale and subtracting the average of the peak timescale at the mirror point in L or at the mirror point in B. That is the point with galactic longitude reversed in sign or galactic latitude reversed in sign. So those are shown in blue and red on these plots here, and the denser the color, then of course the greater the difference between the peak timescale for a given point as compared to its mirror point. So also plotted, if you look very carefully with excellent eyesight, also plotted on the figures are the black Roman fields, which are the proposed fields of view of the galactic bulge time domain survey, Thor Roman. And if you look very carefully, you can see where you should place the fields. So they're shown in cyan, where you should place the fields. Maybe I can indicate with my cursor if you can see my cursor, where you should place the fields to get the maximum asymmetric signal, both in galactic longitude and in galactic latitude. So we can propose two pairs of Oman fields, so they're actually centered on a galactic longitude of plus or minus 9.5 degrees and a latitude of 0, and a galactic longitude of minus 5 degrees and a latitude of plus or minus 1.3 degrees as good targets to try and measure the asymmetry in the longitudinal and latitudinal time distributions respectively. So I should just conclude by saying that most of this work is in a paper led by Sofia Kaczmarek, and we haven't yet put it on the archive, although it has been submitted, and I expect it will appear on the archive sometime over the next month or so. I probably have to leave very shortly to go and give my first lecture, but I can probably answer maybe one question if it's very quick. Or do you want to post the questions to Slack? I'll leave it up to Lukasz.
Okay, thank you very much, Win. I'll use the opportunity that I'm very close to the microphone, so I'll just ask you very quickly, is there an excess of long events in your timescale distribution?
That's a good question. I'm not sure we can really answer it, because I think the efficiencies of the timescale, the efficiencies become very poor at long timescales. So I'm not sure the question can be easily answered with the VVV data. I understand why you ask it. It's an interesting question, and I think we did think a little bit about looking for it, but I don't think this data set is a good one to probe that answer, that particular question. Sorry. Okay,
because that plot actually was missing the x-axis labels, so I couldn't tell where this kind of alleged excess was. But anyway, I would be very happy to look at the paper once it's up. So
well, I think probably we can send you a copy. I guess I probably ought to go and give this undergraduate lecture now. So can I ask if I'm very happy to answer questions, and if people want to post them in the Slack, I should be able to answer them in about an hour's time. I'm sorry to have missed the end of the conference. The beginning was delightful, so I hope the end is as good as the beginning.
Thank you very much, Win, and we'll take over the screen. So thanks and good luck with your lecture. Okay, who's next? Paolo Rota. Let me first share the screen there and find your talk somewhere. And I haven't installed the slide switcher, so
I think this is my position.
I will bring it in a moment, but yeah.
I think now the microphone has to go.
Yeah, the microphone has to go to you.
Okay.
And you will have to press space to change slides until I bring you the magic ring. But you can begin, sorry.
Okay. Do you have popcorn? Yes? Hello everyone, I'm Paolo Rota, postdoc researcher at the University of Salerno. I'm very happy to be here for the second time. So thank you guys to give me this opportunity. Last year in Sardinia, I presented a preliminary analysis of microlensing event Gaia 21 BLX, and now I will show you the final results that we obtained. Okay. Just a few words about microlensing. We know that it's a physical scenario that happens when the light of a distant source directed to an observer is deflected by a massive...
It's getting interference with that.
Okay.
Best located microphone. Somewhere. Yeah, because the speaker is there. Well, let's try it.
Prova, okay. So, what I say? Okay, when the light of a distant source is deflected by a massive object called lens, The result is an amplification of the light signal, and we can see this in the plot on the bottom right. It's called Paczynski curve. It's the famous bell-shaped light curve. The angular scale. Thank you.
Work. I'll move your microphone even further.
Okay. The angular scale of microlensing event is given by the Einstein angle, theta e. In Einstein angle, there are the physical parameters that we want to extrapolate during the analysis about.
Sorry.
Or maybe if
We
you
don't
take
have
the
control.
computer, if you take the microphone and go in front of the, right?
Like that. Sorry. Now you have to sync.
Okay. So in Einstein angle, we have the physical quantities that we want to derive during the modeling or analysis of a microlensing event, the mass and the lens distance. In order to analyze a microlensing event, we need a set of parameters. And the number of the parameters depends on the type of lens configuration that we have. For example, for the single lens configuration, we need 3 parameters: the Einstein time, this time for the source to cross the Einstein ring, the impact parameter, that is the closest approach, projected approach between source and lens, and the time of closest approach. If we have a binary lens, we need more parameters. For example, the projected distance between the 2 lenses, in unit of Einstein angle, their mass ratio, and also the angle between the 2 lenses and the source trajectory. These 2 cases are made considering the motion of the source as rectilinear, but it's very difficult to obtain something with only these parameters. So we need, in order to break the generalizes, high-order effects. For example, we have the thin source effect, that is the ratio between the angular diameter of the source and the Einstein radius, Einstein angle. And if the time scale of the event is very long, we can also include the parallax effect. And we can describe this effect with 2 components along the north and east direction in the sky. And in some cases, it's also possible to detect the orbital motion of the 2 lenses. In our works, we consider the circular motion approximation. It's an approximation we know, but it's okay. And we need 3 parameters for this: the parallel perpendicular and the component along the right-hand side of the projected velocity of the secondary lens relative to the primary lens, calculated at time t0. How we fit the light curve? We use the RT model platform that is based on VB binary lensing codes. It has a set of a lot of library of lectures for all the cases: single lens, binary lens with parallax, and so on. And from this, we run Levenberg-Marquardt algorithm in order to get the preliminary solutions. From this, we run Markov chain Monte Carlo in order to get the best solution. And if these solutions are good, we start to write a paper. And this is what we have done with the Gaia 21 BLX, that is a disk event. Here we have the light curve. On the right, we have the zoom. For this event, we have a dense follow-up made by Omega Key project that it was introduced yesterday. And also the data from the MindSep collaboration with the Danish telescope. I was here a few weeks ago in Brasilia. These are the 4 degenerate models that we obtain from the analysis. The C stands for closed models, while the wide stands for wide model. Closed models are made when the separation between the 2 lenses is less than 1. Otherwise, we have S greater than 1 for the wide models. The sign minus and plus depends on the value of the sign of U0. And we can note that in the table below, we have the magnitude of the source and the blend. And the blend flux is comparable with the source flux. It's very high. blend flux is, we have blend flux or from a background star or from the lens itself, or a combination of these two cases. Since we are in a disk event, the stagger density is lower compared to the bulge. So we did the assumption, the hypothesis, that the blend flux is totally generated by the lens. And that doesn't matter.
I'll move it away.
From the third release of Gaia, we get the parallax with a rho of 1.18. So we assume that the Gaia parallax is the flux weighted average of lens and source parallax. In this way, we have source parallax, lens parallax, source distance, and all the other parameters in function of the lens distance. And in this way, we can try to break the generacies considering some constraints. The first comes from the blend flux. So what we did, we get a conversion in the Johnson V band because we have the mass luminosity relations also for low mass star. So considering also the extinction map of Capitani et al., we have the mass in function of the distance, because we have the absolute magnitude obtained by the mass luminosity relations in function of an apparent magnitude obtained by the models and the distance that is in the modulus distance and extinction. This is the first constraint, mass in function of the lens distance. The second constraint comes from the finite source effect. We get rho star. We derive theta star from using the work of Boyajian. Since the Einstein angle, we can write the Einstein angle as the ratio between theta star and rho star. We have another constraint from between mass and lens distance. And finally, we have also the microlensing parallax constraint. We use the parallax obtained by microlensing that combined with the Gaia parallax give us another constraint. We combine all the constraints together and we get the following plots. We have an acceptable solution if there is overlap between all the constraints, and this happens in 1 sigma only for the closed models. There is just a small overlap in the wide minus model, but since the chi-square of these models is higher than the closed models, we consider the closed models as the best solutions. We obtain this way a binary lens located at 2.2 kiloparsec from us, and it is composed by a G star and K star. The source is probably a subgiant F star located at 2.4 kiloparsec from us. And here this is the plot. We use the Castro-Ginard work for reconstruct the arms. So lens and source are in between the Sagittarius and Centaurus arm. We try also to simulate astrometric microlensing using the latest version of VB binary lensing codes. So it's the orange trajectory, while the blue trajectory is the source trajectory. We can see that during the microlensing event, there are few points of Gaia observation. So since the Gaia baseline is very, very long compared to the microlensing event, we can assume that the parallax measured by Gaia is not affected by microlensing. So the assumption that we did before is good, is acceptable. So conclusion, with the analysis of this model, we can see that the power of Gaia in microlensing is very, very strong, because using Gaia parallax and also the proper motion, because I forgot to mention, but we made the same assumption of a Gaia parallax also for the proper motion, considering it as the flux weighted average of proper motion of lens and source. And we obtain peculiar velocities for lens and disk that are typical of disk stars. So with the fourth release of Gaia, we will also obtain the astrometric microlensing. With the astrometric microlensing, we can get the Einstein angle. So we provide even more information. We will break the genesis more simpler. So we can also get information on stellar population, galactic kinematics, and obtain a lot of useful information from dark compact objects, planets, and so on. And in this context, also Roman, Euclid, and the follow-up, here I must mention Omega and Mansep, because I remember all these two. And this purpose, I'm very happy to include also Salerno, because in the following months, we are ready to reconstruct our observatory that is located in our university. So Salerno is in the south of Naples. There is the Amalfitane coast. I hope you know this wonderful place. So on the rooftop of the observatory, we will reconstruct our observatory. In 2019, a very anomalous storm wind destroyed the dome. We were for 4 years without telescope, but now finally we are reconstruct the observatory. We have a rich criterion of 0.6 meter made by Officina Stellare with the Finger Lakes PL230 with the following features. And we are part of follow-up, test follow-up, Gaia follow-up, Microlensing with Mindstep, and we are very happy to include this telescope in Black Hole Tom. So this is a list of publication made by our telescope, and we hope that we start the observation before the end of this year. Thank you for attention. Grazie.
Thank you, Paolo. In case if there are questions here, then you can shout it, and then please repeat the question so that the people on YouTube can hear it, okay? Questions? Paolo? I have one. And I can say it to you. So I loved the astrometric predictions, and then especially that the method you used for using the Gaia astrometry already with Ruve and so on, right? But then I didn't see the predictions where they were kind of two-dimensional, right? Not the one-dimensional Gaia astrometric time series. Could you show it again?
Yes.
Yeah, this one.
This one.
Okay, this is the 2D projection.
Yes.
Of the position. Okay.
Yes.
But have you included the Gaia scanning angle in this?
The plot are made with in a reference when the lens is fixed. So we consider also the angle obtained by orbital motion of the two lenses. So we assume that the lens is fixed and the source moves in this frame.
I see. So, but this is not what we are going to see in Gaia data.
No.
This is the relative distance astrometric position. What would be interesting to see, and we can probably help with that because we are going to do that anyway, is to essentially generate the Gaia-like astrometric time series, right? So where this is actually the source position we measure. Assuming we know the scanning angles of Gaia, we know when and where Gaia is observing, right? So we can include that, and then the measurements are one-dimensional, right?
Yes.
Okay, that's cool, and I like this plot a lot.
Thank you.
That's cool. Any more questions? Anyone on Zoom? No.
Yes, question. I have one.
Go ahead.
So your fitting code RT model uses template light curves. How do you choose the template to start from?
We have a set of more than 200 we have more than 200 sets of parameters, and from this we start Levenberg-Markov algorithm for each one. So once we get the best preliminary models with the lowest chi-square that we use as an parameter indicator, we run Markov chain from this.
Okay.
Sorry, I didn't mean to interrupt to switch to the other one. Okay, any more questions? Or we switch to another one.
I have one. What's the weather? Not just the weather, but like the sky like in the telescope that you're gonna have? I mean, do you have good nights or like the problems with the light pollution since you're fairly close to cities, right?
Yes, but for transient observation, it's okay. There is no high sky pollution because it's a suburban location, and it's okay.
Okay. Good. Yeah, we're definitely looking forward to see your telescope online again, because it used to be active. Okay. Anyway, thank you, Paolo. And let's move on to Uliana now, who's going to continue on the topic of microlensing. This is the mic. This is the control.
Okay, so hello, I'm Milena. I am happy to present to you in this lovely room. And I work with Professor Łukasz Wyrzykowski on microlensing events. And today I want to show you the events I analyzed recently. They are quite specific, and I try to show that why they are cool. So Paolo made already a good introduction to microlensing in general, but I would like to mention why we do microlensing in our group. We want to explore the population of stellar remnants. So we want to detect dark and massive objects with microlensing because it's also possible to measure their mass. And to measure the mass of the lens, you have to have two parameters, the microlensing parallax and the Einstein radius. The parallax you usually get from photometric curve, but there are more problems with the Einstein radius because there are very rare cases when you can get it just from the photometric curve. And this case is called the finite source effect. Oh no, the keys don't work. Okay, but generally the curves are visible, and it was supposed to show the curve changing with the motion of the source and the lens. And yes, basically maybe this is thought the most obvious case in microlensing, so I will briefly tell about this. In this picture you see the case when both lens and source are point-like objects, and in that figure you see the case when the source, the size of the source should be taken into account, and you see that the curves are a little different because when we have point source we have smaller magnification and more sharp peak. And in the case of finite source, we have the curve with something like a bump. Yes, and the finite source effect should be taken into account when the lens and the source are almost perfectly aligned. So, like when they are very close to each other. And to calculate the amplification of the curve. In the point source, point lens event, this formula is sufficient. But in case of finite source, you have to integrate this expression over the source area. And you see in that formula the rho parameter. And this is just, as Paolo said, the size of the source in the units of the Einstein radius. And basically, this is the measure of the finite source effect, because the bigger this parameter is, the bigger bump we see. And basically, the algorithm of determining the mass using this effect is as follows. So we have to measure the size of the source. We have to measure rho and parallax. Combining rho and theta star, we get Einstein radius. And combining all of this, we get the mass. And what about the events I studied? I selected the high magnification events. So, yes. And the events with small finite source effect, small rho with rho smaller than 0.1. Why? Because as you can see from that formula for ρ, the smaller the ρ, the bigger should be Einstein radius. That was our suggestion, and we want to have as big Einstein radius as possible because we want to have the big mass. Yeah, and we want our lenses to be dark, so we choose the lenses with a high blending parameter. Blending parameter is the measure is a fraction of source light we detect. So when it's equal to 1, ideally, all the light we detect comes from the source, and the lens is dark. Yes, the data comes from BH-TOM, obviously. There are Gaia data, but also OGLE data, ZTF, Atlas, WISE, and many smaller ground-based observatories. And yes, in my case, this algorithm looks like this. I determine the size of the source from the empirical color angular diameter relations, like from work of Boyajian or Adams. I determine ρ and parallax from photometric microlensing, and from all of this I have the mass. But in my case, ρ parameter is so small I can't even determine a specific value. So I just have a higher limit for ρ, and therefore I have lower limit for mass. So here are my events. Some of the characteristic I already mentioned. You see 3 bars, amplification, limit for ρ and blending parameter. So you see the magnification is quite high, with minimum of 3.3 and maximum of 5.1. The smallest limit for ρ is 0.001, and it actually can be even smaller because it's just a limit. And you see that all the lenses are quite dark because blending is close to 1 everywhere. Yeah, and I actually had a chance to check my method because for one of these events, the Einstein radius was measured with VLTI, and its value is 1.2 milliarc seconds. And the limit I determined with this method is 1.1 milliarc seconds. So it's quite reasonable. Okay, to show quickly all of these events to you, I grouped them by the value of mass limit, low mass limit, medium mass limit, and high mass limit. So these 2 events, Gaia 17 IJG and Gaia 21 DPB, have quite low mass limit, more specifically 0.019 and 0.27 solar masses. And this limit excludes the possibility for the lens to be a free floating planet. So it must be a higher mass object. There are a couple of medium mass the lenses with medium limit, about 10 times higher than the previous ones. So here we have limits higher than 0.13 and 0.27 solar masses. And these limits are 0.28 and 0.35. And yes, this becomes even more interesting because now we know that it's not a free floating planet, not a brown dwarf, and was probably not a low mass main sequence star. And one limit is even higher because it's around 1.4 solar masses, so it's about Chandrasekhar limit. And the blending in all of these filters you see is around 1. So we exclude that this is a white dwarf and lower masses objects. So this is quite a good candidate for neutron star or a black hole or a mass-gapped objects if they exist. Okay, so to sum up, from these events I had two limits, two masses higher than 0.15 solar masses, 4 lenses with the mass higher 0.1 solar mass, and 1 lens with a mass higher than 1.4 solar masses. And what am I going to do with all of this? Firstly, I want to look for more similar events and study them and see what happens. And in a longer perspective, I want to determine the mass astrometrically, that is using astrometric microlensing when the astrometric data from Gaia will be released. And as Professor Lorana here said yesterday, we expect avalanche of data, so we have to be prepared. And the analysis like this just help us to determine the most promising events we should study first, at least. So thank you very much.
Thank you, Uliana. That was spectacular. Thank you. Questions to Uliana? Nana.
Really impressive and great. So I was just wondering, how did you search for these events? So I assume you were checking only the ones that already finished, and you went to look at the archival. I mean, did you do the search with? I assume not really with just going through all of the events. So I'm sorry.
I see.
Weird question.
Well, I actually did the search like with downloading high magnification events from Gaia Alerts and looking for Microlensing events among them. And some of that events are found like this. And some of the events were just found, I don't know, by chance. So just looking through BHTOM or Gaia Alerts.
Okay.
They do stick out.
Yeah.
Yeah.
Right?
This the same.
Yeah. There's not many of them.
Yeah, but you were doing manual search, going through it, or you had a code that checked the amplifications.
I had a code.
Okay.
Yeah. But basically one of these events, where is it? This Gaia DR3 lens 067 is from Gaia DR3, so yes, it was found in another way.
Mm-hmm.
Yes, I have a question.
To my ignorance, are there really no very massive objects, dark massive objects that are other than neutron stars or black holes when you get to this very high mass limit?
Can
You repeat the question, then you repeat the question.
you repeat the question?
So you claim that when the lens mass is higher than 1.4, it must be a neutron star or black hole. Are there really no other objects of that mass that would explain the lensing?
Well, as far as I know, no.
Repeat the question because people don't.
Okay. So Ilse asked if there are other objects with a mass limit, with the mass higher than 1.4 solar masses, right? As far as I know, no, because like neutron star have the masses till around 2.1 solar masses. Black holes have masses above 3 solar masses, and there is maybe something in between if it's not the observational effect. But basically, in our galaxy, we expect like only neutron stars or black holes. Maybe we will find something else, something more interesting. But yeah, initially it's like this.
Well, I think we are biased because we still need to find the 100 million black holes which are missing, and only then, once we find them, then maybe we can try to attribute some of these to more exotic objects, right?
So brown dwarfs are not massive enough.
Brown dwarfs, no way. They're below, way below 1 solar mass, right? And we proved these are dark, and also, as Uliana said, 1.4 limit actually excludes white dwarfs immediately, right? So we enter the regime of the exotic ones, right?
Just to follow up, could that be, just a general question to the microlensing community, could these dark lenses be also the strip stars that we find right now in the binary systems, but they can somehow evolve to be a single star, or even like a binary strip star that are not bright enough, but are massive. They're just like
so the question was from Milena if these dark objects could be strip stars. You mean like, but how bright they are? That's the point.
I mean, well, if we look at the binary stars, well, one is a strip star, we don't really see spectra. That was the thing of this unicorn and
Yes,
giraffe,
these fake black holes were proven to be straight stars. Mariusz, we can't hear you. You're talking to Milena or to us?
We will see these bright stars, there will be enough light.
They would be bright enough, you say? Okay. What would be the absolute magnitude of such a strip star?
Minus something.
Minus something. That's bright enough. Okay. Well, white dwarfs are about 10 and fainter, right? In absolute. So.
Yeah, but white dwarfs don't get nuclear reactions. Striped stars bigger than.
So they're brighter. The strip stars are brighter. Okay. Well, that was a good point, and we should definitely keep them in mind. But what is more common, strip stars or black holes?
Actually, we don't know yet.
Well, we just know really a few of strip stars because we were not aware of them.
And we only know a few black holes, right? So.
But we were aware.
Yeah. Well, that's a very good, very valid point, and we should definitely keep that in mind when we publish any candidates, right? Cool.
And let's not forget about hypothetical quark stars. So there are a lot of stuff.
As I said, this is so exotic that we first need to find the most obvious things.
Yes.
Okay. Any more questions? I don't see anything on Zoom. So, okay, thank you, Uliana. And thank you all the speakers in this session. And we break now for coffee for 45 minutes. We resume in 11:15. Thank you. I hope you can hear us well on Zoom and YouTube.
You want to test now with the...
Yes, please.
Okay, and also
But I have to keep Zoom running because then
they brought the table outside. I said, okay.
table for the laptop. Well, we might use it here.
They wanted to bring it during the
Come on. Right.
Do you want to check if my sound works?
Yes. Let's try again my sound. I'll just. Zawołać wszystkich. Kornel, możesz zawołać wszystkich, że zaraz będziesz mówił.
Ja nie wiem, czy ja chcę.
I can go call the people, or are you going?
Kornel is going. 1 minute.
But he's going to.
Cześć Agnieszka.
Cześć, słyszałam, tylko muszę właśnie tutaj sobie coś porobić. Cześć.
A powiedz jeszcze raz coś.
Cześć, ale ja może tego.
Dobra,
Słychać mnie?
teraz cię słychać nas w całym kinie.
Oh, okay. I will mute myself and I will switch off the camera.
Okay. Kornel, you ready? So, okay. Well, does it work?
Doesn't look like it will.
Oh, you have to turn it on.
I think so. How do I do it? Yes, okay. Okay, welcome after the break. And we continue on the fascinating microlensing topic with Kornel Howil. There you go. That's your controller. Boom.
Can I take this to my hand or?
Yeah, you can take it to your hand, yes.
So, hello, my name is Kornel Howil. I'm a student at University of Warsaw, and I will talk about Gaia 18 AGZ microlensing event.
Sorry.
It doesn't work.
Now, try it again.
Okay. So to begin with, the event was discovered by Gaia Scientific Alert on Valentine's Day on 2018. It is located approximately 23 degrees from the galactic center. Its baseline magnitude was around 19.2 magnitudes, which is pretty faint. And in the peak, it was 17.6 magnitude. Here you can see the location of the event with its neighborhood, in a picture generated using black hole DOM. And on the right, you can see astrometric parameters from Gaia. What is important is that UV parameter is high. It was explained in few previous talks that this parameter tells us how good the astrometric fit is. If it's around 1, we can say that the fit is good. And if it's larger than 1.4, we can say that something happened in the astrometry, and we can be sure about these values. And one of the things that could happen is microlensing. Here's the photometric data we have for this event. We of course have data from Gaia, as well as ZTF and SMARTS and a few other observatories. The data from the ground-based observatories, except from ZTF, was processed and calibrated using black hole DOM to standard filters. And here's how it looks on the plot. To model this event, we used only data from Gaia, from ZTF in R filter, and in the V filter, because these are the only bands in which we have data points in both peak and the baseline, and it is needed to properly model, properly fit a model. As Pavel mentioned in his talk 2 days ago, there was done a spectroscopy of this event using X-shooter on the VLT, and from fit of the synthetic spectroscopy, we know that the extinction in the V filter is around 8 magnitude, and the distance to the source is around 11.5 magnitude, 11.5 kiloparsecs. We used Mulens model with MC sampler to fit a model to these data points. Firstly, we tried to fit a model which doesn't include parallax effect. This is the magenta one. As you can see, it doesn't fit the data very well. So we tried to fit a model with a parallax effect. And we found 2 solutions, one with negative and one with positive impact parameter. These are the curves with blue and dark lines. And these curves fit data better, much better, as you can see. Here you can see the distribution of the main microlensing parameters from the MCMC samples, as well as whole numbers describing these solutions. And what is important is that TE is around, which is timescale is around 400 days, which makes it one of the longest microlensing events. And blending parameter is around 1, which means that almost whole light comes from the source star, which means that the lens is probably a dark object. To estimate mass of the lens and distance to the lens, we use the lens code, which was recently used in a few other papers. Basically, we just take MCMC samples, we calculate mass and distance for every sample, and then we use some priors about distribution of masses in the galaxy and velocities to properly weigh these samples. And from that, we get lens, mass, and distance distribution, and dark lens probability, which we define as the probability that the lens is a dark object. That's how the mass distance lens distribution looks like. As you can see, we found two separate scenarios. In the first one, the lens is more massive and is closer, and the second, it's less massive and is further away. To calculate this dark lens probability, we plot blend magnitude, which is the magnitude of the blend light, which means the light that doesn't come from the source star, and lens magnitude, which is magnitude of the lens of the mass in particular sample, in assumption that the lens is a main sequence star. And if the brightness of the lens, assuming it's a main sequence star, is greater than the blend magnitude, we know that it's not possible because we can't have more light than we observe. So the lens must be a dark object. And these two lines are just for two possible extinction levels, because we don't know extinction to the lens in G filter, so we just assume that extinction in the G filter to the lens is between 0 and 8 magnitude. And here's the numbers. As I said, we have two separate scenarios. In the first one, the lens is massive, and its dark lens probability is close to 100%. So since the mass is in one case about 4 solar masses, and in the other case about 6 solar masses, we know that in this case the lens it's a black hole, and in the other case the masses are less than 1 solar mass, and the dark lens probability is very wide, so we can't say much, but it's probably just a star. And what is important is that theta E, which is Einstein radius, in more massive scenario is between 4 and 5 milliarc seconds, which translates to maximal displacement of the image around 1.3, 1.6 milliarc seconds, which should be observed by Gaia. So this could be the cause of so the high RUVA could be this could be the cause of the high RUVA, which we seen earlier. So to sum up, we found 2 different microlensing solutions for this event. For both of them, we found 2 possible scenarios. In the first one, the lens is probably a black hole, and the second probably is a star. And it's possible that Gaia observed the astrometric shift in this event, and Gaia data is in 2 years will reveal this in astrometry. Thank you.
Thank you, Kornel. Thank you. Questions?
So the results that you were showing in the end, they were from your model, right? Especially my main question is regarding the star, but you have a spectrum of the event. So I mean, I assumed you are able to get the parameters of the star from the spectrum. So have you compared these to your results?
Well, from the blending parameter, we know that if there is any light coming from the lens, it's very, very faint. So, and the spectroscopy has very low resolution because this whole event is very faint. So I don't think we can get the information about the lens from.
Yeah. No, I'm
also when you see here, right? So this star solution, it's half solar mass at 8 kiloparsecs. So it's equally dark as a black hole nearby, right? That's our main enemy. Distant main sequence.
And we just turn up for lunch, I think, pretty much. What time is it? Yeah, 11:30. So then we can wander on.
Okay, that was not relevant. Anyway, we were talking about that the main enemy are the faint, distant main sequence stars.
But the spectrum, I mean the star here is the source star.
No.
It's the lens. So it's either like the lens is a dark remnant or a lens. Yes. Okay, I misunderstood this. Sorry.
Yeah, okay, the source is always there. Yeah, no, we know it's a star.
Yeah, right? I misunderstood this. Okay, thank you.
Any more questions? Anything on Zoom? No. Okay, thank you, Kornel.
Thank you.
Let's move on. And the next speaker is Rupak Roy. We changed topic to, well, we stay with black holes, right? I assume.
Still with the black holes.
Slightly bigger ones.
Not slightly.
There you go.
Sorry?
Yes.
Yeah.
Just press here to move forward.
Which one?
Okay.
Okay. Thank you, Lucas. Yeah. So I'm going to talk about the ambiguous nuclear transients. So this is a very new term which has been introduced very recently. So it is ambiguous you understand that there is an ambiguity in understanding its behavior. And of course, it is a nuclear transient. The term was introduced due to the problem in understanding behavior of a particular type of nuclear transient, which is the tidal disruption events. And yesterday, Thomas gave a talk on the tidal disruption events and some outlines he gave. So just for completeness, so if you look at the schematic diagram of a galaxy, the transients which are happening far away from the center of the galaxies, marked by the red stars, can be resolved easily, and there will be no ambiguity. So it is transients by the stars. There may be questions about the type of the transients. There may be questions about what kind of supernova is this, what are the mechanisms behind this. But when we are going to very near to the galaxy, suppose within some sort of 100 parsec distance in the physical size of the galaxy, and the galaxy is a distant, which is a megaparsec distance, several megaparsec away, the problem will be we will not be able to understand whether it is an AGN variability or changing look quasars or microlensing or nuclear supernovas or tidal disruption events or any other unknown phenomena. So out of this, most of the time we are now facing that the problem with the tidal disruptions events and supernovas and some other unknown phenomena which are coming up nowadays. So in general, what is the tidal disruption events? In case of tidal disruption events, the stars get accreted by the supermassive black holes, and which is showing in the left hand side, and it's eventually produce outflow and also sometimes shocks, and depending on your line of sight view and also with on the basis of the surrounding medium, you may see it in the radio as well as in X-ray. But most of the time it is observable in optical and UV. And one of the hallmark of the tidal disruption events is the mass accretion rate, which is followed by the luminosity. It is theoretically predicted it should be T⁻⁵. So it is expected that the decay rate of this tidal disruption process, the luminosity should go as T⁻⁵. It happens in very few cases, like in case of X-ray time scale people have seen, which is in the right side of the right bottom plot. We have seen that the X-ray luminosity varies at the T⁻⁵. It is expected to be it is in the other wavelength as well, because even with the more sophisticated simulations also, it shows that in the long time scale it should follow T⁻⁵. But what has been found that in the optical and UV, many times just after disruptions it does not follow the T⁻⁵. It sometimes follows the exponential laws, and it is also not very clear why is it so. And top of that, we also found nowadays there are events which sometimes are low luminous tidal disruptions, and sometimes this is sharp rising, and there are probably a bunch of disruptions where it is high luminous and slowly rising. So exactly it is not known that what is the reason behind this kind of disruptions. Whether there is a particular role of the environment in this, or it is mainly because of the accreting black hole and the stars. But of course, one of the main thing to know about the tidal disruption events is its spectrum. For example, in case of tidal disruption events, we now used to see the fluorescence line activity, which normally we do not see in case of supernovae. We also used to see the coronal lines, and these are some sort of hallmarks to understand that this nuclear transients is a tidal disruption events. Because the main problem is we will not be able to resolve this particular transients from the center of a distant galaxies. And these lines also change very rapidly. So for example, here is one example. You can see this is a hydrogen line which is marked with the green shade. It is changing over the time. It is initially there was no interaction, and then the interaction started at around 50 days. And then again, probably there was a circumnuclear disk. It is interacting with it. And after some days, at about 100 days, it is crossing that, and the line is again going back to its initial signature, like which was in -22 days. So we have tried to compare it with some of the proposed models. For example, this is with Kassan models with the outflow velocity of the order of 10⁴ km/s. So this kind of things we are used to see with the rapid follow-up using PESTO and other surveys. We also saw a change in the line. The absorption dips change to the emission line profiles at around 4,500 angstrom. So this kind of huge change in the dynamic change in the spectrum we used to see now in case of tidal disruption processes. But the problem is the predicted rate of the tidal disruption event is 10⁻⁴ per year per galaxy per megaparsec cube, whereas the observed is much less. It's the order of 10⁻⁵. And it is not really known that what are the constraints behind this, the low value of this, the measured rate, and whether there is a dependency of the environment and the galaxy, and how it is affecting our observations, and how does it creating in complexity in understanding the TDE science itself. And also top of that, now I will show you some slides where it will show that some of the nuclear transients which initially thought to be a tidal disruptions are now found that these are not tidal disruption events. So these all in total making the complexity in this particular science. So here is one example. For example, Asasan 15LH, which was initially described as a superluminous supernova, and within 6 months, some other people, another analysis say no, these are not superluminous supernova. This is the tidal disruption. Now there is a problem. So even if supernova, if there are two different kind of supernova, there is no problem, because we are understanding that it is at least the same kind of mechanism. But if we are confusing between tidal disruption and supernova, so we are basically confusing between two completely different physics. So physics of supernova and physics of TDs are completely different. And another problem is that TD rate is very low, and it is one example is from IPTF studies. So out of 26, we found out of 493 initial sample, we just found one tidal disruption event. The statistics does not improve much even after ZTF survey also. So this all, as I said, this is the ambiguity. This is the ambiguity created in the science itself. And these are the some examples. For example, this Asasan object 17JZ can be explained as a supernova with a CSM wind, and can also be explained as a tidal disruption process. But here authors then prefer as a type 2n supernovas because of by examining its spectrum and all other things. So the light curve modeling is not enough for to understand that the object is TDs or not. So T to the power minus 5/3 is always not is always not a valid way to check whether it is a tidal disruption or not. Similarly, there is another object Doggy and Asasan 20 HX by Henkel in 2022. He also showed that this is, which was initially classified as a TDs, later found that it is not a TDs and it is rather an AGN properties. We also worked on this particular object for obtaining data for a longer time scale. So here Henkel did it up to 200 or 300 days. So we observed it up to 700 days. And we also did some observations from VLA, Chandra, and we found completely a different scenario, not completely different. So it is supporting Henkel's Henkel's results, but some more insight. For example, this is this is a color composite image of this is the optical image. On the top of that, this radio VLA X-band contour is shown, and the zoomed version is shown this Chandra contour. So initially we were not very sure whether in the center there are two contours, which one is actually the transients, and in optical it is difficult to distinguish between these two, so because of the resolution issue. So we observed it from the Chandra, and we found that the Chandra contour is exactly lying on the center of this object. So we found that so this is the central object is the main transients, which is producing this X-ray as well as UV and optical and radio. We found that its radio component is very low luminous. So this below two blue dots are basically the two observations, radio observations from for these objects, and it has been compared with a different radio luminosity from TDs and also from radio quiet AGNs and all the Seifert galaxy central component. And we found it is, and also the all radio supernovae. And we found that its radio luminosity is really very low. So essentially it is a very low luminous object. Maybe it is a very low luminous AGN, extremely low luminous AGN. top of that, what we found from the spectrum, that this blue spectrum, if you see the right plot, the blue spectrum at the bottom is the SDSS pre-explosion spectrum, and if you add some black body, you can do some sort of minimization technique, you can fairly reproduce the transient spectrum at a different epochs. So essentially the transient has no extra features, spectral features, which we believe it should have if it is from a disruption of stars. It should have some emission line feature due to hydrogen, helium and all those things. So it is nothing like that, it is just a black body. We, for example, we did these observations for up to 700 days, and we find out what is the luminosity variation over the time, and the radius variation, and also the temperature variations. We divided into 3 parts. So this is in the bottom panel and in the left side. You can see we have shown the phases. So at the early phases, we found that the temperature follows the R to the power minus 0.47 law, which is the blue dashed line. Whereas in the late phases, temperature follows R to the power minus 66 this law, and the solid black line is showing the Sakurai-Tsunaev disk model. So if it is a Sakurai-Tsunaev thin disk, it should follow T to the power T is proportional to R to the power minus 5 by 7. So it is basically R to the power minus 0.75. So most likely there was a thin accretion disk, very thin, very primitive stage, and it was in turbulence and in the early phase when the transient happened, and over the time it's slowly cooling, settling down towards its actual stage again. We did the full ACD modeling, taking the data from SWIFT for both UV optical as well as X-ray and radio observations from VLA. We assume that this is which I've shown on the right side. We assume that the system is in a very primitive stage. There is no torus, there is no very thin disk, there is no BLR. So I put some crosses there just to show that in this model, I'm not assuming those are things. There is a very primitive disk, and we found that the emission, which is basically UV optical emission, is basically the disk emission as coming as a black body. And top of that, there is a blob-like emission is coming out, which is actually the source of the entire emission starting from radio to X-ray due to the synchrotron. So the important thing is the X-ray, it is synchrotron. This is synchrotron self-absorption in the radio, which is actually optically thick, whereas in X-ray it is optically thin. But it is the same source, which is basically that blob, which is emitting. So it is some sort of new blob coming up due to that transient process, and it is producing this. Coming to the host of this transients. So if we understand the host, want to know about the host of the transients. So extensive work was done by French and Thomas. So they have shown that these hosts of these TDs are basically a fraction which is between the stellar mass is between 10 to the power 9 to 10 to the power 11 solar mass, and this is and their star formation rate are also is actually different in comparison to the regular galaxies. And Henkel showed that their AGN activity, they are quite different from the regular AGN activities. But we should also remember that when the galaxy evolved from a star forming stage to the AGN dominated stage, there may be two channels. One is the top channel, is basically the channel where the AGN is not embedded within the dusty medium, and the bottom channel when the AGN is embedded within the dusty medium. So essentially, if the TDEs are happening within this highly embedded dusty medium, UV optical surveys will not be able to detect the TDEs. We will be only able to see those TDEs which are happening in the top channels. So this is maybe one reason this is a fraction which are getting a very few factor less of observed TDEs, and it was very nicely demonstrated by Seppo in his paper in 2018, where they found a TDE in a very obscure, dustly obscured medium by doing the IR observations surveys. So the IR surveys are also very much important to understand whether this disruption events is happening in the lower branch or not. Otherwise, we will miss many such nuclear transients. We are also trying to understand the same thing by improving some sample size. So we have taken about 60 samples, and so in this sample, in the rightmost panel, you can see the different telescope from where we have taken the spectrum. We have used the spectrum taken from those telescope, and also their magnitude, G magnitude and absolute G magnitude. So they are very tight. In the absolute G magnitude is very tight, and we can see that so this is mg minus 23 is one of the brightest transient maybe observed by the ZTF and other surveys. So if such kind of transient, if we put at a different redshift, what kind of magnitude, absolute observed magnitude, you will see that has been shown in the red curve. And whereas minus 17 is the faintest TD is observed from ZTF, and whereas there is a black dotted line which shows that the upper cut of the ZTF limiting magnitude. So you can see that if we want to study some sort of volumetric estimation, so understand that in how many fraction of this total TDs are actually low luminous and how many fraction is the high luminous, we should be constrain ourselves within the yellow strip in that plot. Otherwise, we will actually biased by the Malkowitz effect. So these things we are now. This is some work which is going on, and some of in one of my student is working in her MSc thesis. Not moving.
Interesting. We can do it. Oh. Okay.
Okay. So what we have done, we are basically using a PPXF code, which used to first we took those spectrum of those galaxies where TD happened early, and we used the PPXF code to actually segregate the galaxy component and the star component, stellar component, and then she tried to find out what are the average absorption lines are there for the emission dominated system and the without emission dominated system. So basically absorption dominated system. We found that there is no highly much difference in the spectrum, but what we do found that their spectral equivalent width of those systems where there is no emission line is much higher, which shows that probably these are those systems where star formation happened and now it is quenched. So these are basically the post star burst galaxies, and these are now star forming galaxies. And we further found the supermassive black hole mass of these systems, And these red regions are those low luminous, these are the black hole mass of those systems where low luminous TDs have been found, and blue are the host of those others. And we found that our results is more or less consistent with the previous results shown by French. So it is around 7 solar mass, 6.5 to 7 solar mass around that. So this is the most of the TDs are happening. Further, using the emission line, we found out in the BPT diagram what are the different characteristics of those emission lines. And we found that most of the TDs are happening in the absorption dominated system, and much less in the emission dominated system. Among the emission dominated system in the star forming region, there are more in comparison to AGN. So there may be effect of line of sight, and how we are looking. This is on the basis of geometry, it is also affecting. So we are actually working on this direction. So the some take home message, though essentially the TDs are very rare events, and there may be an issue due to our observational issues are there, and there may be an issue due to the geometry and the environment. There are events which are showing both TD and supernova features. To know about them, we need much high precision astrometric observations and modeling of light curves, and those things are required. Particularly to 2020 HX we found, which is consistent with the Henkel results, that this is not a TD, this is rather transient process happening in some low luminous AGN's disk, which is at its primitive stage. Some more will come in my paper, which is under review, will come soon. Yeah, so thank you. Okay. And before stopping, I want to show one thing. This is the our institute. So this is the main building where and institute is now promoting for more collaborative work. So they are very generous to host for at least 3 months, even more than that. Faculty from outside can go there and can stay for as a sabbatical. And good thing is we have sea within 10 kilometers. We have mountains, so that is the Western Ghats mountain. So if you want to go to sea, also mountains, so you have within 10 to 50 kilometers. Okay. That's great. So that is my contact. You may talk to me or contact. Okay. Thank you.
Thank you, Rupak.
Any questions?
Questions to Rupak? Ilse.
Yeah, this is all very interesting. I have tons of questions, but I'll start with the simplest one, I think. So the blob you're hypothesizing, did you also look into turbulence in the disk itself? Would that be an explanation for the transient that you see there, and to get the condensation of material in the accretion disk? Or do you really need something to be moving away from this?
So
please repeat the question, because people on Zoom.
So your question is, I actually did not understand. So your question is whether the blob is required to.
Yeah. So what we see in event horizon telescope, especially in our own galaxy, is that the disk is not stable. The accretion disk has thicker and thinner regions which evolve very fast. And I'm just wondering if something like that could be the case in this source as well, or if you really require a moving element away from the accretion disk.
Okay, so in this particular model, actually, this is JetSet model we have used. So in this particular model, let me go back. So in this particular model, we assume that this emission is the blackbody emission is coming from the disk, and the synchrotron emission is actually coming from the blob. So now this is a very simple model. We can you can think much more complex scenario. So at this moment we did not think about that. Yeah.
But you don't have radio data where you actually see, like in the classical AGN, where you see jets.
No, actually this AGN, this system is radio quiet, X-ray quiet. It was before this transient. After that, it became X-ray luminous, radio luminous. I put some proposal in VLBI to see that what is the situation now, but I don't know, waiting for the comments or acceptance.
Okay, we have a question from Michelle on Zoom.
Yes, hello, Rupak. You mentioned that the majority of your hosts have absorption lines and no emission lines. So the question is whether there is an active nucleus in the center or whether an inactive AGN or whether it is due to obscuration. So my question is, do you have X-ray data for those hosts to show what is the column density toward the center?
Okay, thank you. So we yet working on this. So this is basically your this one, right?
Yeah.
So we did not check the X-ray data. So it is I mean, this is at this moment the student work on the I mean, just by looking that there is no strong emission line, assume it is an absorption dominated. So we are basically working on, so these all the absorption, the system marked as an absorption feature dominated are really absorption feature dominated, or there are some small lines are also not there, or there are X-ray emission from there or not. So we are actually working on it. So yeah. So
okay, thank you.
I don't have any good answer on that.
Okay, thank you. I'll just, I won't let other people ask questions because I will ask a question just from the kind of observational point of view. What would be your advice? Because we haven't had any TDEs or any nuclear transients in BH-TOM yet. These are challenging, I know. Typically they are faint. They're also embedded in the galaxy sometimes. So they pose some observing challenges. But do you foresee any use of BH-TOM and our network for your actual work?
Okay, good question. BH-TOM will be helpful, of course, but the main problem, what I said, in all cases, probably we are looking the upper branch, because after there is not only this particular suppose object, there are other objects where we found the radio emissions. Actually, I have a program in UGMRT to see the radio follow-up of the transients. But the thing is, for all cases, we saw the UV optical emission as well. So that means these all objects are actually going through this upper branch. Okay, so maybe we need to do some IR survey kind of thing, which is actually very difficult at this moment.
So you're saying that we should be finding more of these in infrared.
We should find more on these. So these are obscured. I mean, if these are obscured.
Yeah, and for that we need first we need the survey, and then we need the infrared follow-up as well. Right?
Yeah.
Okay. So
I mean, this is my opinion. Maybe if you have some.
We do have some infrared telescopes in our network. We haven't used the data extensively.
No, but the thing is
to find it first.
Finding first is required.
I know.
So most of the time, what we do the follow-up. But the finding is in this upper branch.
Yeah.
So essentially that is the problem.
Okay. But anyway, I still see the use of our network, especially for that these events, they last months, many months, and you don't need the high cadence observations, right? In general. So these are kind of relaxed mode observations.
One of the thing, maybe, I mean, I will be interested because I'm now working on this host part. So if we can find out that how the transients are going, so depending on that, we can do the host, I mean, we can take the spectrum of the host to do this analysis. So how this host, whether the host of the low luminous TDs are different from the host of the high luminous TDs or some other properties. So there are other properties like what is the line of sight extinction for these cases. Most of the times we consider there is no extinction of the host. Okay, so but that is not exactly correct. Okay,
Of
so
course, of course.
so that is some areas. But,
For that you need spectra, though.
yeah,
right?
that is so that is the reason I'm saying. So using BA storm, we can first understand that okay, this object is a TD. So we are not in this analysis. We are not working on the TD. Actually, we are working on the host galaxy of the TDs. So we need just a spectrum after that. But first of all, I have to know that that is a galaxy. And that's it.
Okay. Okay, thank you, Rupak. I have to move all the other questions to lunchtime, for example. And now we have another talk, which is on a very different topic. We will continue this topic, this exciting topic, after the lunch break. But now, since we are in a cinema, we'll make a good use of it. And let me find my mouse first. Okay. Is it the first slide? Yes. Yeah. Milena will tell us about something equally exciting.
Yeah. So hello everyone. Hello again. It won't be probably so exciting as the movie that is in the other room, as we can hear from the sounds. But I hope but there's gonna also be some movie or video at least. I'm going to tell you about the GaiaVari Citizen Science Project. It's a project that was already mentioned by Laurent yesterday. But using the opportunity that we have some time, I wanted to introduce you to this project in a bit more details, since we are all from various universities and we are also from different countries, and we are all approached by some people who would like to be involved more in astronomy, but they don't have their own telescopes. So during this conference, we've heard some talks about using like a cheap telescope for doing citizen science or science by citizens. And this is actually the first project that uses the Gaia data that is called the Citizen Science Project. It's funded by ESA and is also supported by ESA staff and people working with the Gaia mission itself, including the CU7 coordination unit, which is the one that is the unit in Gaia about the photometric variability studies. So the main idea of GaiaVari obviously comes from Gaia mission and variable sources there, is to support the classification of variable sources there. So as we know, we have a lot of variable sources in Gaia. They are classified, as we've heard yesterday from Laurent. They are classified by machine learning, but it works really well, but it's not perfect. So sometimes we still need an eye or a finger of astronomer or a citizen scientist that is trained well to distinguish in between where the source belongs to. So basically, the main goal of this project is, apart from outreach and educational effort, to actually check the classification for Gaia DR3. So to check and give a feedback for the classification and to create the very pure sample for classifiers for DR4. So we really need, so we know that the source is classified, let's say, as a error Lyra, and we check if the citizen scientists classify it the same. If it's classified the same, then it means it's a good classification and it's in this pure sample. I see someone is moving there, Alex. And then, but if it doesn't agree so then we can, it's suspicious. And also this is very important for having some extra interesting sources that basically are not visible in the standard classification. So because we miss them. So if we have something super interesting, it's not classified and we don't know it's there. So if we look at the eclipsing binary, you know it well, but I wanted to point your attention into one thing. So if we look obviously at the light intensity, light curve to the left, it looks like this when we have an eclipsing binary. But what Gaia gives us is also the changes in the color. And this is the second plot. So you can see actually the color changes this way. It's actually obvious, right? Because like we see these two legs. We have one change of color when we see one component and another one and another component is here. It's obvious. But I mean, I was actually surprised to learn that actually the color changes looks like these two legs. So basically, if we look only at this color changes, we could say it's an eclipsing binary because it has two legs. So that's a nice thing that you can do with the Gaia data, not only light curves, but also this kind of things. But if we look, for example, at the pulsating star, the color changes look like a loop because the star pulsates. So even if the light curve of, for example, some eclipsing binary of a binary itself, let's say semi-detached binary, is very similar to some pulsation star, we can look only at the color changes and distinguish in between these two types. So and that's why Gaia it's so basically so rich in the data. So here it comes, the citizen science project. We know Gaia doesn't give us nice images, so it's pretty difficult to go to the citizen scientists, to the people, internet users saying, okay, well, we don't classify nice images from Hubble telescope or from, these are not nice galaxies that Galaxy Zoo was using. These are just like, data points. But we use this very famous Zooniverse platform that for anyone who was active in citizen science project, you know it well. There is a link, so if you want, you can log in and you can check it on your own. And basically what we see 4 plots. These are the changes of the brightness of the source. This is already folded light curve with a given period of the star. So this is something that we have from Gaia DR3. Then what we have here is a color magnitude diagram with a zoom, and then the position in a galaxy, which is not super important, but actually gives some additional information and looks nice. So basically, and we have like four variable classes that we can choose in between. And from the period, from the shape, and from the information in the tutorial, we should know that this star is what? I will check your knowledge. What is this star? Mariusz, I'm sure you know. It has just 10 hours, Yeah, it's our Lyra. So yeah, well, anyway. So that was the first campaign. And the second one is even more complex. More complex because we don't have four classes, but we have 6 classes because we added delta scuti and ellipsoidals. And it's everything written in a tutorial, how to deal with this data, how every kind of like class should behave and so on. And for this one, well, okay, I can tell you it's an ellipsoidal. I won't ask it again. So yeah, it's an ellipsoidal, and that's how it works. So basically, if you know, you click. If you don't know, you click none of them. And then if you need some help with this task or you want to comment it, then you click done and talk. There was, okay, I just cut it, but it's there. And it's a nice discussion going on. So we have 977 users. So if every of you join the project, we will have 1,000. So that would be my nice request to you. A lot of classifications, so more than 300,000 classifications. In the first campaign, we have 10,000 objects. Then in the second campaign that is running right now, we have almost 21,000 objects, a lot of comments. And actually, the initial first campaign was completed in 3 weeks. We were super, very, very surprised that it went so well. But there is something that we call retirement threshold, and it was actually set up to 10. So it means that 10 users has to classify the source to make it already classified. So we have to bump it to 20, and it took more time than to actually have it. So language versions, several language versions. So also thanks to Uliana, we have also the Ukrainian version of this. So this is basically in various languages, which is nice for the community because not everyone knows English, especially in the Spanish one and so on. So I really encourage you to use this GaiaVari, and also if you want to create, I don't know, like Bulgarian version, or if we have some other people who would like to join, and we would be very happy to help in that. There is also a GaiaVari.space webpage where you can find some nice handbooks with information, astrophysical information, some nice set of posters. There is like a map where people are actually joining the project. You see most of them are like Europe, but it's also a lot of AVSO people joining us, and also some people from India and so on. The big peak in the usage of the webpage was actually when the first campaign was open. So we do some online training sessions. So if you are interested in having introducing GaiaVari to your community, you can approach us. That's the one actually with the with the Polish astronomers, well, how do we call it, like amateurs society. We get some on-site workshop during Festival of Science, some TV shows, magazine, and all of the users, all of the active users get a certificate that is actually signed by ESA and signed by CU7. So it's signed by Professor Laurent Ayer and is signed by Professor Pedro Garcia Lario. So these are people connected to Gaia, both from side of the coordinations unit and also the ESA. So interesting cases. So we have several very, very dedicated users. Very dedicated users means that they classify every day, I would say like hundreds of sources. So it's a really, and they comment it and they check it. They check it, for example, and also in Simbad and something like this. So we have dozens of intriguing cases that were missed actually because of the classificator, and we have some examples of our Corona Borealis stars, some misclassifications. What surprised us was that actually people started to tag something that we didn't really ask them for. So there were some, it can show you the level of some of these amateurs, that actually they started to notice that there is a Blaschko effect visible in the Cepheid light curves and so on. So, and also they started to do some tags for subclassification of Cepheid, Lyra, and so on. So that's very, very nice, and actually that gives us a lot of attention. Okay, so there is a social media coverage of that, and as a very last thing, I have a short video. I hope it's gonna work, and maybe it will wake you up a bit in this cinema mode. Let's see. Okay, thank you, and I'm happy to answer any questions later on.
Immediate questions, comments, Nada?
You kind of almost answered this, but I still wanted to know, so for the languages that you mentioned, so what's the process of, accepting another language to the possibility to, change it? Is this easy or it's, complicated?
Yeah, since we don't know all of the languages, so for example, you say you want the Slovenian version, we have already the framework ready for putting new things. So you get into Excel file that has an English version, then you put all of the Slovenian version, and when you say it's accepted, we just basically put it to the Zooniverse, and there is also a framework ready for that. So basically, we cannot do the translation. What we can do, actually, we can do the Google translation, and you could be the one to check if it's correct. But very often, it's actually easier that if you do it, then then that's how it works. But it's immediate, so basically, yeah.
Good. Thank you. So now it's time to spend some time with BHTOM. So we have some time, well, not much time before lunch. So if you're interested in playing with BHTOM, you're invited to stay. If you know BHTOM very well, you can go for a swim or for early lunch. So I would encourage everyone interested, well, we call it kind of hands-on session, but it's actually going to be me presenting some stuff. But if you're, well, I would encourage people interested to come closer to here so that we can have some interaction and discussion, okay? So the way I'm going to do this, I'm going to start BHTOM. And I think what we will start with is, I don't know how to do that. It's not the most convenient place to be. So first of all, the link, it's not what I said yesterday. Actually, the bhtom.space is the link which takes you to the newest version of BHTOM. You can either use new BHTOM or just BHDOM, and that will bring you to, okay, it doesn't work. Sorry, it was supposed to work. But anyway, you can still find it. So this is BHDOM 1, but here, if you click here, then it transfers you to BHDOM 2. Okay, good. So I see, as you can see, I'm already logged in. I assume you can all do that as well. So the first thing we will start with is, I'll make it bigger maybe. Okay, we'll go to the target list. And so let's assume you have a telescope, right? That was the case posted by Asha yesterday. So you have a telescope and you want to make your observations. You're going observing tonight and you would like to know what is there of interest. You don't have any particular science cases in mind. You can observe whatever. So essentially, this is the place you would go for. So you go to the list. Of course, you can try figuring it out from the map, but why? If you can just filter it, right? So if you scroll down here, you can go, well, you just go to the coordinates. And let's assume our telescope is located, Asha, correct me if it doesn't, why? Białków. Okay, so we have a telescope in Poland. So first of all, we will probably don't go further down than declination 0, more or less, right? And then we want the priority, which is actually, I hope this is not the priority, it's the importance. So typically this is the value between 0 and 10. And well, we all have to settle how to set these things up relatively, but this is of course relative importance. Typically from BHDOM 1 experience, we typically set it to 4. Everything above 4 is kind of worth observing more or less now. If anything is below 1, it is also requiring observations, but maybe it's much more relaxed and it's not so urgent. So let's say we put it above 4, and then also we can very crudely limit ourselves to sources which are currently visible, right? So this is the simple sun separation. It's not the actual visibility of the object, right? You would need to check that carefully later. But if you set it to 60, I think you should be fine for most of your targets. And then, of course, the magnitude, we can set it to what, Asha? Which magnitude do you want? 16, okay.
18.5.
Przemek is more ambitious. Let's do it ambitious, 18.5. Okay. There you go. From BHDOM 2 alone, it's a small list so far. You have this one target, you have the coordinates for it. It's 13.8, so it's very bright. It's of high importance, and only then, well, you see it here on the sky, right? And you can click on it and then see how it looks. What is it doing? You can zoom in, see what has been observed. So we kind of, from the light curve, we can tell it's a microlensing event, but it's already kind of in its late phase, let's say, right? If kind of from the experience we've had, I would say this is the target of, we should probably lower the importance of this target as we see it now. Typically, we detect these microlensing events on the rise here. This was probably the Gaia alert which triggered it. There has been some ZTF observations before. So what is most crucial in microlensing events is you observe before the peak and after the peak until it reaches the baseline. But as mentioned by Kornel as well, we need some baseline observations. It's equally important as the observations during the curve, right? So if you have, so that's kind of a lesson as well. If you observed the event somewhere here, then it's also crucial to have some data points at the baseline. Of course, there is less urgency for this because you can do it whenever the event is going to stay at this level. But of course, the sooner you do it, the more information we have, and the sooner we can start working on the publication. So this is a crucial point to take. If the microlensing event is over as you see it now, and you haven't observed it there, don't bother, I would say, right? It's going to be waste of your observing time. It's not going to bring any important astrophysical information anymore, right? But if you have observed it here somewhere early on during the curve, then it's actually very important to collect the baseline observations, right? So equally, your data taken here at the very peak, even though it's perfect, it might carry no astrophysical value until you collect the baseline observations. This has to do with the way we derive parameters for microlensing events, like blending. The whole model is actually relying on some relative changes in brightness, and especially that we're dealing with different telescopes, then the blending factors changes. So we need to figure out the blending parameter for your instrument. So that's why we need data from both kind of periods. Okay, of course, this is a microlensing case, right? There was one case called Gaia 22 BPL where the importance was high and people kept observing the event even though it was already at the baseline. Maybe I can quickly find it. Maybe it's already there, actually, in the system. By the way, do you know this is very useful here, which was not there before? You can just type in the name. Okay, the data is not downloaded here yet, but we can see it already in Gaia. If you look into BHTOM1, we're still transferring the data, so don't worry about this. So this was the main peak of the event, but then it did it again, right? After a couple of months. So if we had switched this event off here, no one would notice, except this one guy at that point. That would be useless for us in terms of astrophysics. However, we have beautiful coverage of this peak, the second peak as well, simply because we forgot to switch it off, right? So you never know with these microlensing events. Typically, they don't repeat, but that's an example of a case when it did repeat, and it's actually very, very interesting event. Okay, we have some data here. Data is coming, as you could see, but it's coming from most recent to the oldest one. Okay, so that was one of the stories, right? You can of course go to visual list as well, right? Since we have it here, we can, for example, select only microlensing events, and that's it. So we can now scroll. You see, this is the event Kornel showed. This is FKL, which is probably going. We are probably going to switch this one off after something like 2 years of observations. This is a beautiful event, and we have plenty of data. So that's going to be a very nice analysis. This is Gaia 19 DKE, the very famous one showed by Marius. This one should also be switched off soon because we probably don't need any more data for this. However, I wouldn't mind if you keep observing that one because we don't know what it's going to do. Okay, so these are the microlensing events we have so far in BHTOM 1. So you can use this filtering efficiently. Well, we will add more fields here as we speak, so you can select different fields as well in terms of galactic coordinates, for example, and stuff like that. Okay. Any other? Yeah, one thing I wanted to show is, you see, after we have filtered everything, the web address contains your filter. So you can actually bookmark it for yourself or just copy paste it. And next time you open the page, especially for the previous filter I showed, you can just enter the address and that will give you the most recent list of observed targets of interest. So that's one of the ways of storing this. Okay.
Priority here is priority or importance?
Yeah. So that's
here the importance field is
1
between 2.
Yeah, that's an error I fixed already, but it's not yet on the server. Yeah, so previously we used to have priority here, and then the observing priority here, right? So and that was causing confusion. So I created even more confusion now because I just called this importance, and the observing priority is just priority. So in the filtering, after well, probably this evening, the filtering will give you the importance, right? We thought, well, you will be able to filter on this as well, but this value, I will say it again on this occasion, actually. This is a value which is computed based on the importance, and then the last data point, which we have in the database, regardless where it came from, right? So for example, if the target was observed by Gaia just 2 days ago, and the required cadence for that target is also about 2 days, then the priority of that target goes down, even though no humans on the ground were involved in taking the data, right? And then in other scenario, if the object was high on the list and someone observed it, uploaded the data, and the data is there, appeared there in the system, the target drops down in the list because it has been observed. Although you can use this list to look for targets, but I also strongly encourage you, especially as I described for the microlensing events, once you start observing one of the targets, keep it going, right? It's gonna be, your data is going to be way more useful if you keep your targets observed for a long period of time, right? Of course, you can observe them only until they are visible. Of course, we can't overdo that. However, even though you see some targets of high priority there, you should still maintain your own list. Once you add your target to your queue, keep observing it until it's not interesting anymore. Okay. Any other cases? Fabian.
The name of the target, is that specified by the user who adds the target, or is that some automatic archive?
Yeah. The name is, it could be anything. It could be my favorite black hole here, right? You can name it whatever you want. You can name it after your dog and something.
But and this is the name used for the link.
Yes.
Going to the page of the
exactly.
target. Okay.
Exactly. So this is the kind of a unique name, and it could be anything. And then, well, typically, we keep it's kind of useful to see that it came from Gaia, but only when you click on this event somewhere there, say here, then you see it's called this way in Gaia alerts. It's called this way in other surveys. So you can equally add a ZTF target with ZTF name, but if it happened to be also in Gaia alerts, we will find it, right? You don't need to even know it, right? So it works both ways. And then vice versa, Gaia alerts are being looked into ZTF database as well. We will add Ogle, MOA, other surveys which produce alerts as well. Okay. Yes, I will make a comment about this photometric classification because I haven't had time to show this before. This is something what we published with Ilknur Gezer a while ago. There's a paper on arXiv, not accepted for publication yet, but the system is online. There is actually if you want, I can give you the link to that, but BHTOM is doing this. So we query all archival information we have on that location from Simbad, from whatever is there. And we're trying to build the SCD. This is something what was shown yesterday or 2 days ago using VOSA. Our system is probably less complex than the VOSA one. And here it works for any coordinate. You just give the coordinate, it will give you the best guess. So here, the source was classified as a red giant with 93% confidence. I would say that's pretty good. If it's above 90, then it's trustworthy. If it's below, then don't look at it, even don't bother. So for microlensing events, this is actually quite crucial. So we can distinguish YSOs, B stars, which might look very similar to microlensing events, especially at the early stages. So the classifier doesn't look at the light curve at all. It is only using the static archival information, whatever is there. So that might be useful for some filtering early on if we don't know even what the target is, and you want to help us classify it. You might, for example, pick these objects which have very low probability. So we have no idea what it is. If it says it's a red giant, but a very low probability. So these targets, we don't know what they are, and we probably need long-term photometry for this. Of course, if you can take a spectrum, that would be the ultimate way to solve the issue. Yes, another.
Can I comment just on this classification? I think this only works with stars. So if you have extragalactic, it's gonna still say it's a specific percentage of the star or microlensing event of the giant. So this really works just for the stars.
Yeah, because by definition, while we are kind of assume the extragalactic transients, they don't have any archival information, right? Unless it's located on top of a galaxy, right? But there is no entry for this.
Yeah, what I want to say is that, well, you will get like an entry in there, but because the output of this code was based and used for stars, so you don't have classifications for anything other than types of stars.
Yeah, so this is very yes. So this works best within the galactic plane, let's say, for sterile-like alerts and targets, right? Yes, Piotr.
How is the class for the event? Because like above the photometric class, we have class unknown.
This class,
put in manually?
Yeah, this class goes, well, this is this field, right? So by definition,
you distinguish between unknown and not yet classified.
So this is actually this alert came from Gaia Alerts. So when we query Gaia Alerts system, this is reading what Gaia Alerts is saying, and for many cases of Gaia Alerts, this says unknown, even though actually by looking at it we know what it is, right? But there has been no spectroscopic classification. It's a complete. Well, Simon Hodgkin he might explain you more about this because he's behind this. He's manually adding the classes into the Gaia alert system, and he has his own criteria, and he's doing it in his spare time as well. So that might be the limit here. In many cases, the class by definition is just unknown.
So here it's downloaded from Gaia Alert.
Yeah, by default, it is. If Gaia Alert says something, then we try to figure it out. We put it here. If Gaia Alert says it's a supernova, we say supernova, right? If Gaia Alert says quasar, we say quasar. In most cases, it says unknown, but we can then change it, right? We can change it to microlensing event. That's it, right? And we can then go to save, and then there we go. I'll ignore the message there. So now we have it as a microlensing event here, right? Okay. Yeah.
Is there any way to search for only the bumps in the area? That will be the connection with what I see.
Yes.
I don't have anything in the UV applicant. I want to check whether there is a bump.
Well, our system is not meant for this. So you first need to have some kind of a target. You have to create some target. So you can create your target of interest, and then it will download the data for you. Then you can look into that. So you can.
Maybe all EPF this dusty galaxy, multi-galaxy. Yeah.
Okay. Well, the way I would suggest you could do that, so you could import your list of targets of interest. We will get the data for you, and then you download all the data, and then you process it by yourself in your own way. Unless you want to propose something we add to the models, we can add something to the models. And yeah, this is still kind of a feature in development. In future, we would like the modeling part to be as of support for planning observations, right? So, for example, automated checking if the event is over, especially for microlensing events, and then adjusting the priority given the model. So This is almost there, but it has low priority on our working list. But this is something what we can easily add here. I was thinking about your TDE models. They can be added here as well, right? And then the supernova model we mentioned with Alexander. Okay, any other use cases I need to show? Anyone on Zoom? No. Okay, so let's stop here. I hope it was useful. And then if you have any questions, how to use it, or you encounter some problems, then let us know. On the Slack workspace, there is a dedicated BHTOM2 channel. So become active there. And let's stop here and let's meet after lunch at 2:15. And we might watch some movie here since we're in the cinema. If you have any ideas, what should we watch? Keep it legally. Thank you very much. People, it's time. Jeszcze 3 minuty. I think I'm sharing screen. Whoops. Możesz. Masz slajdy do zmiany?
Proszę?
Masz slajdów kilka?
2 slajdy, ten i następny. Dobra, ten środek to jest laser.
Lasera nie używaj, bo tak odpowiadać. Okay, welcome after the lunch break. So let's begin our very last session, the most exciting one. And we start with Basia Handzlik.
Okay, hello everyone. I'm Basia Handzlik from the Jagiellonian University, and I'm working on comets. So we are going closer to the Earth right now. And I wanted to talk about some possibilities that observing comets with a network of telescopes. So we already talked about asteroids, and contrary to asteroids, comets have very elongated orbits. So, and they are mostly active during very close approach to the sun. So we have the first constraint that the comets are active for a very short amount of time, and this is one of the examples of time domain astronomy. And one of the things that we can observe with comets is we can do photometric observations, but it's also not that straightforward in case of comets. Because they are very extended objects. So first we have to choose some good aperture, and this aperture can change with time depending if we want to probe the physical surrounding around the comet. So this is the first challenge if you want to, for example, include comets in the BH dome system, that we have to have a changing aperture. So we can track the activity of comets during their approach, but the comets are very unpredictable objects. And for example, we can have large outbursts. This is a very interesting object of a comet that brightened by 15 magnitudes in less than 48 hours. So we have very peculiar situations, and it's very important to do photometric follow-ups in case of that situations. We also have some newly discovered extra solar objects that are worth to perform follow-up if we detect any more of these objects. The other very catastrophic thing that comets can endure is spontaneous disruption and disintegration. Mechanism and consequences of this thing is not fully understood, and one of the main reasons of the spontaneous disruption is believed to be a rotational spin-up that can lead to the disruption of this object. So when the comets are close to the sun, the sublimating material is creating jets and torques that can drive the angular acceleration of these bodies. But contrary to asteroids, we can't observe the rotational period by just doing photometry of the nucleus, because most of the signal from the nucleus is dominated by gas and dust coma. So what do we do? We can do observations with millimeter wave spectroscopy, and that's what I'm doing right now, is analyzing the time variations of the brightest lines in cometary spectrum. Here I observe the HCN molecule, which is sublimating directly from the nucleus, and is giving us very precise information about the behavior of the nucleus. The advantage of this method is that it's very sensitive, and it has a very good spectral resolution, so we can track not only the brightness of the lines, but also the shape of the lines. The disadvantages is the accessibility to the instruments, because in case of tracking the comet rotation, we need to have very good time coverage. The other thing is observing the daughter molecule from the HCN is in the optical range is CN, morphology. So we use the narrowband filters, and we detect just the changes in the CN jets. So this method is more accessible, but still not many telescopes has these narrowband filters. So to change that, there were some tests of the shelf easily accessible CN filters, and the tests went very successful. It was cooperation between amateur astronomers and professional astronomers, and it turns out that this kind of filters produce similar results to these professional HB filters that are very, very expensive and not easily accessible. So there are a few challenges that this produce, because these filters have some contamination in the ER part, but it creates some possibility to use more telescopes to observe the rotation, and more importantly, rotation changes. We have a lot of measurements for the rotation of comets, but only few measurements for the rotation changes. So here comes the possibility to use the telescope networks to have better time coverage of this phenomena, because we have to have time coverage of the full, not yet known rotational period, and we want to track this rotational period throughout the different stages of comet apparition or the window when the comet is visible. So this is that's why I would like to encourage people to observe comets, and if anyone would be interested in implementing these narrowband filters in their telescopes, then let me know. We can discuss about the possibilities that will be the best suitable for your telescopes, and also how to purchase them. The challenges are also that it's needed to have a camera that is sensitive in near UV range, because it's at 387 nanometers. And also the big challenge is to have non-sidereal tracking to make observations that are at least a few minutes long for the fainter objects. And later I would like to include these objects also in BHTOM, and this would be very good test for the non-sidereal objects in BHTOM, and I think we will have to implement some of the new features, and also it would be nice that we have the access to FITS files, for example, in BHTOM in this case. Yeah, that's it. If you're interested in cometary science, let me know.
Great. Thank you, Basia. So we don't have time for questions, but Basia is here and you can ask her on Slack. What would be interesting for me is to find out how difficult it is to do photometry of comets, because they have, they're not point sources, right? So that's probably a challenge. And that's going to be a challenge for us. Okay, good. Ashwin, can I ask you here, come forward and tell us about an exciting target? We're coming back to black holes, I hope. Maybe 2, maybe 1. We'll find out, right? Okay, hold this and hold that. I'll hide your slides. And yours is yours. Bank. Okay.
Hello everyone, I'm Ashwin. I'm a master's student at Nicholas Copernicus University in Toronto, working with Dr. Carolina, who most of you know. And in case you guys are ever bored of all the beaches you visit, Toronto, exact center of Poland, there's absolutely no sea. So feel free to.
There's a river.
Yes, there's a river. Yeah, so I am working on a very interesting source, which was originally termed as the TikTok source, which may be a binary black hole, supermassive binary black hole system at the center of an active galactic nucleus. The first group that studied this object was in China, and they submitted the paper to Nature, but it got rejected. There's a long backstory. This on the left is the field from Aladdin, and on the right is a picture from the telescope in Pivnica at Toronto. Yes, the original team had predicted that there is a supermassive binary black hole system at the center, which was due to merger around now, maybe. I don't know. And they were followed up by another group from Italy, from Milan, .tm, using the La Silla Observatory in Chile. And both teams independently ran post-Newtonian simulations, but arrived at different results. According to the Italian team, the original paper did not account for energy losses through gravitational waves at a particular point in the orbital phase. So they actually found out that the amplitude fluctuation would increase, which means we have increasing period, exact opposite to the first group. So we thought it would be interesting to see what the photometric follow-ups would look like. And so we needed more data. And Black Hole Tom gave us a lot more data. So it became my job to filter through this. It still is going on. We have observations from over 30 telescopes, and that's not counting AVSO and VVS. We even have observations from the Pivnica telescope, and that was calibrated and uploaded to Black Hole Tom by Carolina. And so at first we split our data, the fresh data from BHTOM to 3 epochs that we could see clearly, and sticking to some of the observatories that had the most contributed data points, we could see some pattern, but not good enough to no distinct period was found. The Fourier spectrum was just not, we got nothing from the short-term study. And this was in multiple filters, we saw the same situation. But when we proceeded to take in the ZTF data, the one in blue, and stick up our new data from Black Hole Tom, we started to see a very long-term pattern and a short-term pattern. So the cadence from the ZTF data was around 2 days, so we could not account for nightly variation. And meanwhile, all the observatories that contributed to Black Hole Tom, we could see this clear fluctuation every single night of like 0.2 magnitudes, which is not trivial. Something could be happening in all the bands from all the observatories. So we try to bin the Black Hole Tom observations to have a day-wise like median binning, and compare to with the ZTF observations to see if we have any long-term behavior that was clear, but nothing yet. And I'm still working on getting more observatories calibrated and adjusted to the same level as the ZTF to see if there's any behavior. And another thing we intend to do is using because we still have the raw data from BIMNITSA, we would perform independently the photometry and compare what we get with the black hole term results as a safe sanity check, maybe. And yeah, we yet to see what would happen. Hopefully we make some conclusions.
Thank you very much. I must admit this is the most challenging target to study. And there is a question from Alex online.
Hi, thanks. Hope you can hear me okay. Yep. So yeah, this object was interesting when it made the headlines a couple years ago, but the original group did not attempt to make any null hypothesis simulations with regard to whether it can just be ordinary red noise. They only had like 3 or 4 cycles, I think, and ordinary red noise can do that. And so I think the work you're doing is absolutely critical, because when you only have a few cycles, more data is always the correct answer, as we know. So this is absolutely critical work that you're doing, and I applaud it. And definitely shows that resources like the optical networks and Black Hole Tom are quite critical as well for getting the new data to test these models. And so I also want to encourage you to conduct simulations of pure red noise, because it's certainly not difficult to set that up, and I'm happy to talk with you offline to talk more details about that.
Oh, thank you very much. Yeah, that is something we hadn't looked into yet, but yes, it does make sense to have that checked.
Cool. Any more questions, comments? No. Okay. So we kind of looking forward to see the final results, right? And then we encourage people to keep observing the target, right?
And thank you so much, everybody who's observing. Thank you for all the work.
Okay, thank you very much. Let's move on. So Carolina has a comment. You can comment while we switch the slides.
Yes. I would like to tell you that it was like a very tedious work, because there is like a huge amount of observations, and the job Ashwin did, which is right now not like perfectly visible, is writing to code, try to filter any kind of data. So I think this is like the starter you are right now seeing, and let's hope we will show you like some kind of conclusive results next year.
Thank you. Let's stay with the topic of black holes, nuclear ones, and then let's see what they do in terms of flaring from Nada.
Thank you. Hi, everyone. I'm Nada Ihanec. I'm a PhD student at Astronomical Observatory, University of Warsaw, and I will talk about part of what I'm doing in my PhD thesis, which are studying nuclear transients. In the beginning, I want to quickly talk about the Gaia alerts and nuclear flares. So as many of you know, since 2019, Gaia became more equipped to search for slow rising targets. A lot of them were nuclear transients. Hence, from 2019, there was a really big increase in detecting nuclear, all the nuclear, transients, obviously. So you see on the right, there's it works. So I plotted the number of discovered already classified the alerts. So in the beginning, you see we have the total number, which is in the gray. It was less than 100 up until 2018, and then all of a sudden in 2019 we do really have 3 times or 4 times more discovered AGNs, quasars, and BLX. I wanted to show this because I think I kind of always do it with the numbers of the alerts. So as you can see, compared to the last year, there were 5 new AGNs. And in this case, I just want to clarify regarding AGNs, BLX, and quasars. So these are the classifications that Gaia provides, and they are only these classifications are if the increase in flux happens in the target that has previously been classified. So with SDSS or any other streams. So yeah, we do see that there has been increased with the number of published alerts, as we know, and as well as the different types. Under unknown, I want to say that like approximately 10% of all unknown Gaia alerts are nuclear targets. So why am I interested in studying the centers of galaxies? And there are two reasons. One of them is to study black holes. So we do know that the only way to really study the supermassive black holes in the centers of the galaxies is either with measurements of the position of the stars, as was done with the gravity collaboration, and or as we've seen also yesterday, the first image of the black hole with the Event Horizon Telescope. So this was really the only way to study the properties of black holes. The other one is with AGN variability. It has also been mentioned in the talks yesterday and today a little about this. So it is believed that depending on the position of the angle that we see, the AGN, you get different types of different types of AGNs. So one of the problems with studying flares from the centers of galaxies is to actually determine what the nucleus of the galaxy is. So here I'm showing three different examples of the galaxy with the cross inside is the location where the alert was occurred. So in the right cases, the right two cases, these were the Gaia alerts. You can see there is a big difference. So the distance here is the distance from the location of the alert compared to the center of the galaxy, the host galaxy, and the coordinates that I chose for the center here were the either SDSS coordinates or the coordinates for VICE. You can see that the distance from the nucleus was in the top case 11 kiloparsec, in the bottom almost 40 kiloparsecs, and both of those were tidal disruption events, classified tidal disruption events. In the case of this one, this was technically based on the coordinates closest one to the center of the galaxy. However, it turns out it was a supernova. I think it was type 1a, and as we know, this has not the reason for the explosion of supernova 1a had nothing to do with the black hole in the center of the galaxy. So it just happened to be so close to the center. So the possible nuclear alerts, the ones that are actually connected to the properties of black holes, are the AGNs or the changing Klug AGNs, tidal disruption events, boron fluorescence flares, maybe some microlensing phenomena is not really connected with the properties of the black hole, but this is the reason why, for example, you would have a nuclear flare or change in the nucleus, and then we have some new phenomena that has not been discovered yet. So just quickly, what is a tidal disruption event? I'm not sure if it's going to work, but this is a simulation done by Tai Jankovic from University of Nova Gorica. I hope you see here a star. So when a star comes too close to the black hole, the tidal forces become stronger than the self-gravity of the star, so the star gets disrupted. And then depending on the properties of the star and the black, mostly the star, part of the debris can accrete back to the black hole, and the rest stays away. So that's the reason why we see these flares. They are one of the most luminous flares, and they occur in the galaxies with masses of 10 to the 6 to 10 to the 8 solar masses. They're very luminous, very hot. The temperature stays constant through the whole flare, and in the spectra they show blue continuum with broad helium and or Balmer lines. And in recent years, we started realizing that this is quite a heterogeneous group. So there are many different types of disease. The second of the possible nuclear transients are Balmer fluorescence flares. So these have been discovered only recently. We see the flare from the center of the galaxies, and in most of the cases, it happened in narrow lines every one galaxy, so in active galaxies. And what happens is that we have increase of the optical UV emission, and this triggers the photons from Lyman alpha-like transitions of helium-2 at 300 angstrom, and this then triggers and excites states with the similar energy, and it creates cascade of transitions which show as the lines described here. And this was well established in planetary nebula, but not really in X-ray binaries. So, and again, this is another way to study the central black holes. The next case, or the last case, the type of transients are changing Hugh quasars. So here we do see the change in the light curve. So the AGNs typically, in optical at least, they don't really vary by a lot. And there have been cases when all of a sudden you have increase for more than 1 magnitude, which is really not normal variability. And when people compared spectra from, you see, like within 10 years, you do see change in the Balmer lines from broad lines to narrow lines. And again, if you remember this plot, right, the difference between narrow line and broad line regions it would depend on the viewing angle. So this is not really clear how this happens. So because of all of this, I decided to do study of flares from the centers of galaxies in Gaia alerts. So my main criteria was that the flare happens in the location of, so the location of the flare, is the nucleus of the galaxy. There is small or non pre-flare variability, so I did not exclude AGNs, and there's no repeating flares, and the flare itself has to be at least 0.5 magnitude. So I got time on INT to observe 35 targets, so in 2021, and then February and April 2022. I also want to mention that in the last 4 years of my PhD, we also have 7 different targets for which we had other observations. But in this talk, I just want to mention that the fact that we do have them, but I'm not really be focusing on this. And of course, to do the proper studies, we do have additional photometric data, which was added to this analysis through the awesome black hole TOM, as we all know. So yeah, I'll focus on this. So these are just the location of all the targets, and I must say that I took this a screenshot from the black hole TOM. So if you have your targets in the black hole TOM, that you can plot them in the nice field.
But you can switch off the moon and the sun.
Oh well, this I didn't know. Sorry. Yeah. So this is the position of the moon and the position of the sun. But yeah, I didn't realize that you have this option.
So we can read out when was the screenshot taken.
Well, yesterday. But yeah, I really do like this feature for the presentation purposes. So
but also I want to comment, your galaxy is kind of twisted.
Yes, so
you can also switch to galactic coordinates.
So I did assume this, but I was in slight hurry, I must admit. Okay. So I was playing with the movement, because you can also like move the galaxy, and this was the best I could do.
You can also add the lines,
grid,
they're horrible. Yes. So this is the new Aladdin version 3, which has all these nice features. So they're all available.
Yeah. So it is really useful, and I wanted to show it because I'm not sure if it was. It was shown, but I wanted to show that you can do this for your target. When you create target grouping, you can just plot all of your targets along. So this is, I know it's a lot in a big table, but what I wanted to show here is the redshift range. So it's from 0.018 to 2.75. So we do really have a big range of targets. For 2 of them, the bottom 2, the problem was that I was not able to determine the redshift because the spectrum was just noisy or like really weird. And some of them have, so when there's the line with SDSS, they do have SDSS archival spectrum from 20 years ago. And as you can see, not really all that have SDSS spectrum are, or no, actually all of them that have SDSS spectrum are classified in this classification, it was from Gaia. So I wanted to show some examples of the light curve, the different times that I had. So in this case, it may look like, there was like a short flare and then all of a sudden it's back to the baseline. I observed this spectra just before it got back to the decline. So I could not predict that, this is not going to be a long-lasting flare. And really, for 4 of them, we also have first detection. So they are radio sources. We then have slow increasing light curves, or like slowly increasing fluxes, and then some weird variability when you get just increase and then decrease. This looks debatably symmetric, and really prominent and nicely visible flares when you have 2 magnitude increase. This one was in 1 year, and then you have decrease in more than 3 years. And then I think 2 examples that I have to show. So this one was, it has the 2 magnitude rise in 2 months, and then it's been decreasing for 4 years after that. You can compare here with the WISE observations, with NEO-WISE observations, and there is delay. I believe it's 1 year of the delay. So that means that the NEO-WISE, this gives information of the size of the dust storage. So you really can study well with the data provided from, and all of this is taken from Recol-Tom. And the interesting part here, at least for me, is that we believe that this is a case of Balmer fluorescence flare, because you see these nitrogen 3 and helium 2 lines, and then the oxygen 3 here at 3100. And but however, there's a really big contamination from iron. So all of this is area of iron as well as here. So I have to do more study of this one, well, for all of them, but that's basically what I'm doing now. And yeah, here you see comparison, really like the length of the decline, and it's still, after 4 years, it still is not back to the baseline. And if you remember from here, right, there was, yeah, this unfortunately doesn't really have good observations from Catalina, but at least in NEO-WISE, there was no flares detected. And then this one is, I still wanted to show you with what I meant in the beginning when I said that you can have supernova really close to the nucleus. So I believe that this one was a supernova flare or some other type of flaring that this galaxy did, though it's not AGN. So I do believe it was a supernova, because we had the time of the Gaia detection was 31st of October 2021. The next one here, sorry, I don't know why here it didn't write 2022, but anyway, so on 1st of May was this point, and I observed the blue spectrum few months in the months in between, and as you can see, there is no real change except for the increase in flux and some broadening of H alpha, but you don't really see. I think I have to do the proper course subtraction, so maybe we will see some supernova here, the signal of supernova, but yeah. But you see that there was no variability before in the Catalina. And so yeah, to conclude, we have a really big diversity of nuclear flares, nuclear transients, which was shown not just by my talk, but also in the talks before. And we start to discover really peculiar objects in recent years. Some of them were already mentioned today. And that it's a challenge to find good model and mechanisms behind these explosions. So I do encourage people who are doing the modeling to study this in more thoroughly, and I'm happy to share the data, and I'm looking forward to seeing more and more alerts from this. So, that's it. Thank you.
Questions, comments? Przemo.
I have this one question about the slide when the black hole eats the star.
Yeah.
What percentage of the whole mass can be eaten up?
Okay, so the question is about this with the tidal reception events.
With the TTEs, yes.
Yeah. So I will play it again because I really do like this.
Beautiful, yeah.
The model, the animation. So the question was what percentage of the star gets accreted and what percentage stays away. So this depends.
What percentage will be eaten.
Yeah,
not,
yeah.
Not accreted.
Yeah. So the question is the change, like the percentage of accreted material and non-accreted material. This depends on the properties of the star that gets disrupted, and also the how close to the white part here is the tidal radius. So if the star comes within it, it's going to be disrupted. If it doesn't come within it, it's not going to be. So the percentage of the disruption depends on the properties of the star, how close, how inside of this gum. So there's a lot of different reasons.
Can you estimate based on the brightness of such flares?
So
can you estimate the size of the initial star?
Based on the way that the light curve looks like. So the increase in light curve, it will tell you it's proportional to the mass of the supermassive black hole. And then I think the decline rate can be fitted. You can get the properties of the star and how much has been accreted and disrupted based on the yeah. Sorry, I can't hear to repeat, but yeah. But you can get this from the modeling of the light curve.
Ilse?
Yeah, I was intrigued by the scores you showed where the growth lines changed.
These ones?
Yes. So is this something that happens repeatedly, or is it just once that this has been seen in this source?
So I think in all of these cases, so this is taken from Paolo Rota, and when he was studying the changing quasars. So if I remember correctly, you do see, so you see I'm not sure if they observed if they compared the appearance and then disappearance, but I do. So I think I know that in all of the cases, in the cases you see either increase or decrease. I'm not really sure if they then, because these observations were done in 2017, 2016. So it's been now five years since then. So I don't really know how, if they observed them again to see if it changes again. But I do know that these changes, like when you compare the sizes, when you calculate the full width have maxes of the Balmer lines, it's really hard to explain why and how this is done. I mean, what kind of mechanisms behind are.
Well, I want one very basic explanation would be that your torus is not uniform.
Yeah. So yeah.
And then a trick to work around that is to do spectropolarimetry, because then you can always see your Balmer lines in polarized light, because they still get reflected into the other side to some extent.
Yeah. So yeah, the comment I'll just try to repeat is that to try to observe these changing blue quasars with the spectropolarimetry to see the changes. And I have been discussing trying to do this with the telescope in Crete when they're doing spectropolarimetry of TDEs, and I kind of want to push these ones as well, so to compare. But that's actually a really great point, and we have been talking about this, that the changes for these changing quasars could be because of the torus itself, right? Yeah.
There is a question from Michelle online.
Yes, hello. Just on the last point, it's very difficult to do polarization because there are very few instruments, but the Force 2 on the VLT is the only one having a good polarimeter, so maybe you could try there. My comment is, or my question is about your last slide, the object, the 21 AFM, if you can show it again, please.
Yeah.
Yeah.
Oh, wait, something.
Yes. The next one, yes. When you look at the light curve, the way when it is up, it's quite longer than a typical supernova. And on the spectrum, the fact that you see a broad H alpha appearing compared to the reference spectrum looks to me like it's a changing look quasar, isn't it?
Okay, yeah, in one hand, I would say so, just because of the strong oxygen lines, right? Because they are my understanding is that the oxygen, like around 5,007, is typical for AGNs.
Yeah.
That's not for me, but
So Mariusz said that there are also star-forming lines, which I thought that this galaxy was, that it was a, I forgot what was.
Yeah, but one is not exclusive of the other. It can be majority a star-forming galaxy, and then when something is happening which you do not understand, you have a broad line appearing, and that's what is called a changing look, you know.
Yes, but the reason why I haven't considered this option is because if you see here, there is the change in H alpha. However, oh, sorry, there is a, well, but the lines are written there, right? So there is a change in H alpha. However, when you look at H beta and H gamma, they didn't get broadened, right?
Yeah.
So
okay. Maybe
so
some
I,
information also. Yes.
yeah, I would assume that if this broadening occurred because of the accretion, that you would see the same broadening in all the rest of the Balmer lines. But I will look into this more.
But and in any case, the light curve seems to me much broader than what you typically see for a supernova, you know. So
sorry. Yeah, what is not clear here, and I didn't say, and I apologize for this. So these lines here, so the black points are the points from Gaia, and the red ones, the red and magenta, well, the darker red, they are detections from ZTF. So if you can see on the bottom, these are different filters. So yeah, so sorry, yeah. So it's not that it got brightened, but so ZTF didn't detect any flare.
This is just the galaxy observed by the ZTF.
So this is just the galaxy.
Okay.
Yeah, I apologize.
Okay, thank you, Nada. I'm afraid we have to move on to another related talk given remotely, and I let Alex the screen. Alex, you're there? We see you.
Yep. Okay, so can you see everything okay?
Yeah, everything is fine. Yes, the screen is yours.
Okay, thank you. First of all, thank you very much for allowing me to give a talk to present work on what our collaboration is doing. And thanks for allowing me to give a remote talk. Sorry, I could not attend in person. So we'll be talking about some interesting transients that we've discovered in the X-ray band, courtesy of eROSITA and its all-sky surveys. And I'll be talking about some of the multi-wavelength campaigns on a few individual events. So let me time is short, so let me dive into it. Okay, so changing look AGN or in quasars, or we also call them changing state AGN because they might be driven by big changes in the accretion rate relative to Eddington. These have been discussed previously, including in the last talk. They usually you have a big change in the continuum flux, and that drives changes in the flux of the broad lines, as has already been discussed. These objects are neat because it helps probe accretion structure as a function of accretion rate and different types of disks. They could be analogies to black hole X-ray binaries in our own galaxy and outbursts and decay. So these are objects that our collaboration has been interested in trying to identify with eROSITA's scans, as I'll explain in a minute. But we're also interested in radioquiet Seyfarts that seem to show transient flares. Those might be an indication of some sort of disk instability. Some collaborators of ours in the eROSITA consortium at MPE are working on TDEs. We're also interested in TDEs that are occurring in already active galaxies, which these are objects that seem to show the observational properties of both TDEs and AGN or quasars. There's a big famous example, 1ES 1927 from a few years ago, where it seemed like the X-rays, as you can see in the middle panel, basically disappeared for a few hundred days, while the idea is that some sort of TDE-like accretion may have disrupted the inner accretion disk and the X-ray corona, and it took a few months for it to gradually rebuild itself. And so these are the types of objects that our collaboration is interested in. And so let me introduce eROSITA. By the way, I should just point out that I'm an external collaborator working with the eROSITA, German eROSITA consortium. So eROSITA was launched in 2019 into L2 orbit aboard a Russian platform. Its goal is to monitor the entire sky multiple times to map out large-scale structures, but the fact that it can scan the entire sky every 6 months means we got time domain astronomy in the X-rays. And it could basically monitor about 1 million extragalactic point sources in the X-rays. And as I said, it scans the entire sky every 6 months, enabling X-ray time domain science for about 1 million AGN. It had completed 4 1/3 all sky scans before it was put into safe mode in February of 2022. And by comparing the X-ray fluxes between the 6-month scans, we can detect if there are major changes in flux, basically as these events are occurring. As opposed to, say, looking through archival data from years ago and detecting things serendipitously. And what our collaboration likes to do is to dedicate multi-wavelength follow-ups for selected individual targets, so we can track the response and the formation of the various accretion components, the disk, the corona, the broadline region. So basically, how we do it, and this is a slide from our collaborator Dave Homan. Basically, we have detection algorithms that include cross-matching with Gaia and by eye verification. And we do have, like I said, we initiate follow-ups both on the ground and in the sky for optical spectroscopy and photometry and X-ray and UV with, for example, XMM and SWIFT. Managing all of the data is a bit of a challenge. And so David actually created a private database to help manage everything, which contains all the new follow-ups as well as archival data, for example, the points from WISE and ATLAS. And so basically what we do is we want to dedicate follow-up resources to, say, the top few hundred candidates for optical spectroscopy to verify if there are changes in the broad Varma line fluxes compared to archival spectra. And then we actually have confirmed about 80 or so changing look AGN so far this way. And a few dozen sources, we can basically, the ones that are the most variable, the most scientifically promising, we can devote the full multi-wavelength resource package to try and track all the various components. We really do need simultaneous monitoring in X-ray and UV and optical in order to get the full scientific picture, ideally with cadences down to days or weeks at least. And so the rest of this talk is going to talk about a few of these multi-wavelength campaigns for just a couple of selected targets of interest. And so the first is the most X-ray luminous extragalactic transient so far in ERAS. This is a paper that was published earlier this year, first author David Homan. On the top, we just show for fun the eROSITA images showing that from ERAS 1 to ERAS 2, you have a big, huge burst, and then it fades over the next year or so. And the X-ray flaring, this occurred in late 2020, which coincided with optical brightening and a plateau and a decay detected with Gaia, and there was a Gaia alert in late 2020. The bottom panel shows the various light curves from Gaia in dark blue, ATLAS, which has been really helpful for us in orange and cyan, for example. And we also look at WISE as well to see if there are any dust echoes. And this particular object we think is a TDE in a low luminosity AGN. So all the follow-up campaigns we did, follow-up observations with XMM and NICER and SWIFT and optical spectroscopy showed some characteristics of a TDE, including a very soft X-ray spectra and a very rapid flux decay. And left is the multi-X-ray instrument light curve. But optical spectroscopy, it looked like an AGN. We have broad Varma lines with, interestingly, a transient blue shifted component indicating some sort of transient outflow, as well as the usual AGN emission lines that seem to indicate that this is still an AGN. And so our best interpretation of this object is a TDE in a low luminosity AGN. Another object, this is so I'm showing here the light curves. Top is X-ray in black, middle panel is Atlas. So this is an object that the soft X-ray flux blasted upward over about a 6-month period and then decreased over the next 6-month period. And this is an object that was already a persistent and stable regular Seyfert. So this is a soft X-ray flare in an already persistently accreting nearby Seyfert. And so we applied follow-ups with XMM and NICER and optical spectroscopy. Due to time constraints, I can't go into the details, but our broadband SED fitting suggested that the main cause was some sort of disk instability in the inner disk, which caused continuum flaring in the optical and UV, and that drove soft X-ray emission via thermal compensation. The fun part comes in the optical spectra. So what I'm showing here are 3 optical spectra over the course of about 6 months. And these spectra are simply overplotted, scaled by the continuum, not by the constant O3 line, simply to show the change in the equivalent with the broad helium-2 line, which was very prominent, but then rapidly faded over the course of a few months. So maybe this could suggest a physically distinct origin than the hydrogen Balmer lines, probably a lot closer in to the black hole compared to the Balmer lines. But it's also consistent with a scenario where the line responsivity of helium is simply stronger than that for the Balmer lines. This is work being done by my former PhD students like Krupa Krishnan. It's all work in preparation and the paper is to be submitted soon. So simply for the purpose of I know it's only a 15-minute talk, so just to put up advertisements for some of the papers that are either published or in preparation for our top few objects. Number one, I already talked about a TDE and a low luminosity AGN, and this has been published earlier this year. So it seems to show characteristics of both accretion channels simultaneously and suggests that the boundary between these classifications of TDE and AGN accretion can be somewhat blurred. So if you're interested in that, I encourage you to read David's paper. And I mentioned the flare in the radioquiet Seyfert, Krupa Krishnan's paper in preparation, where we have a very strong soft X-ray excess changing and the changing of helium-2 line. A third object will be talked about in the next talk by Tathagata Saha. This is another object where a flare was detected in eROSITA and ZTF, and we'll talk about what we found from that. A couple other papers just to finish up very quickly. I think I'm running low on time. If you're interested in partial repeating TDEs, then I really want to encourage you to look at Xu Liu's paper from earlier this year, where we have an object where the X-ray luminosity varied by literally orders of magnitude, and the follow-up campaigns indicated transitions between a thermal-dominated state and a corona-dominated state, which meant that we're basically witnessing the formation and destruction repeatedly of an X-ray corona. So that's a fun object, and I encourage you to read Xu's paper. Very, very last thing, completely different type of object. We're looking at, we're interested in changing obscuration Seyferts, where these are Seyferts where clumpy material associated with either the torus or disk winds can obscure the soft X-rays temporarily and lead to major changes in the soft X-ray flux. So I'm actually leading a paper on that that was submitted for a changing obscuration Seyfert. So other objects that we discovered before the shutdown, we're still continuing some of our follow-up monitoring programs, constraining response timescales, and hopefully eROSITA will be started up again soon if conditions permit. And when that happens, we will absolutely be interested in additional follow-up observations, including optical photometry, for example, with the various networks. I hope I did not run over on time, but yeah, thank you for listening, and I will stop there.
Okay, thank you, Alex. I think for the interest of time, we'll continue with Tathagata now, but thanks for this talk, Alex, and we're looking forward to alerts from you, which we could contribute to. Okay? Right, so we stay in the topic. The screen is yours.
Okay, good afternoon. I'm Tathagata Saha, a fourth-year PhD student. We're working with Alex, and today I'll talk about a multi-wavelength study of a flaring changing look AGN source with a double-peaked Balmer emission line observed with both eROSITA and the Zwicky transient facility. So this work has recently been submitted to Astronomy and Astrophysics. So before I go into the main results, again, a very brief introduction on changing look AGNs. So large changes in flux and which is tied to drastic changes in broad emission line properties of the sources. So so this helps us understand big questions, and assuming that these are not driven by obscuration, intrinsic obscuration in the sources, we can investigate what the typical length of an AGN duty cycle is and what could be the cause of such large variability, for example, instabilities in the accretion disk. So this source was detected in 2020 as a flaring source in the G and the R band in the Zwicky transient facility, and this flare was found to be tied to a large change in the broad emission line properties. For example, here, this broad H beta line, which was initially absent in one of the archival spectrum, has appeared. So this is visibly a double-peaked spectrum. However, the H alpha was kind of persistent previously and has intensified in the new spectrum from 2020. So this was a type 1.9 to type 1 transition. So this flare was also associated with other changes in other bands. For example, a large change in flux in the X-rays and also in the ultraviolet. There's also a broad flare in the infrared, as seen here from the WISE light curves. So so all of this indicates that this flare has a multi-wavelength signature. So we observed this, we continued monitoring of this source for 3 years, and we have collected a lot of optical data from different observing facilities. So here is the plot of all the optical data that were collected over 3 years. So here we have the first observation from Keck after the flaring, and this spectrum shows a blue continuum towards in this part of the spectrum, and this continuum is seen to subside over 3 years as the flare decays off. So towards the later period of time, we see that the spectrum is only dominated by the galaxy. Also, the H alpha emission line, which was found, which was always seen, was found to be variable. So it just varies in intensity, whereas the H beta emission line, which was strong towards the beginning of the transient, kind of decayed to almost match up with the baseline continuum. So also other emission lines like the narrow O3 doublets, and the nitrogen 2 doublets can be seen. This source also exhibits a weak sulfur doublet here. So we perform a detailed modeling of all of these spectrum, and we find that for the continuums subtracted spectrum, for the line residuals, a single Gaussian component is inadequate to explain the total profile. So we have double-peaked emission lines. We have double-peak. We use double Gaussians to model these emission lines, and also for the narrow emission lines, it shows evidence of a potential outflow because there is a broad blue shifted component. So modeling over 3 years, we find that the emission line fluxes kind of vary in concert with the continuum, as shown here. And this could be the indication that the continuum from the central engine is kind of affecting the broadline emission very strongly. Also, we performed detailed modeling of the source with a much more physical model, which is the disk line model, which taken from Chen and Halpern, and this model helps us estimate the properties of the broadline emitter. So we find that a single disk line was not adequate. However, when we add a Gaussian, the fit improves by quite a lot, and we can estimate the emitter geometry from these fits, and we find that this emitter is kind of localized within a few hundred gravitational radius to 1,000 gravitational radius almost, and is seen at an inclination of almost 15 degrees. We also perform modeling, phenomenological modeling with the failed radiatively accelerated dusty outflow model, or the FREDO model, and this is one of the more physical models of the BLR. So in this model, in the outer BLR is sustained by dusty gas being accelerated by emission from the central engine, and when it rises up, it gets sublimated due to much more intense radiation, and the matter just falls back onto the disk. So when it rises up, that part of the matter serves as the BLR. And the profiles that are seen in this model depends very heavily on the black hole mass, the inclination and the metallicity of the system. And so this model currently doesn't have proper radiative transfer implemented. So we just perform a phenomenological broadening of the kinematic profiles that we have, and then we fit to the data, and we find that this is quite the model that is consistent with our data is mostly corresponds to up and down trajectories of the motion of the gas, which means and the whole system has an aspect ratio of about 0.01 almost, and both disk line and FREDO indicates that the broadline region is in this object is consistent with a flattened disk type emitter. So also in the X-rays, we find no indication of intrinsic absorption, and also no evidence of the most prominent soft X's, which is seen in multiple CIFARs. The power law index is consistent with to be around from 1.7 to 1.9, which is evidence of hot quantization. Also, because soft excess is absent, we can make the following conclusions. So probably a warm corona, which in the warm corona prescription for the explanation of soft excess, it means that the warm corona is probably absent, and also when this is modeled, when this is thought to be ionized reflection, it could be understood that the inner accretion disk is probably truncated, and reflection is probably minimum. So there are a few evidences evidences against this transient being a tidal disruption event. So the light curve is pretty symmetric, and we do not see the typical abrupt rise and T⁵ decay. And also the X-ray spectrum is pretty flat, which is generally an indication of an AGN, and as TDs mostly have much steeper slopes of the X-ray spectrum. Also, there are strong narrow emission lines present, and with that we make DPT diagrams, and we find that this is the source is basically localized in the AGN region. And other indications, like for example a transient helium-2 or a Barn fluorescence is absent in this source. So the most plausible model which we think could have driven this flaring it could be disk instabilities in the accretion disk. For example, there could be radiation pressure instability according to the Lightman-Yardley model, where when radiation pressure exceeds gas pressure, there could be outbursts. Also, a recent paper by Shnigovska et al. Have theoretically modeled the light curves which exhibited multiple flaring. So this event could be one of the parts of these flarings that are seen that has been theoretically calculated. So we find that this estimation of timescales from these flares, we find that these are mostly consistent with thermal timescales, and the parameters can explain such a flaring driven by an instability model. So the overall conclusion. So we think that the main cause of this flaring could be due to this increase in luminosity could be driven by an instability which led to more photoionizing continuum. As a result, the H-beta line appears, changing its type. And now, when the flare has disappeared, the flare has subsided. This source is now returning back to its baseline state of type 1.9, as the quasar continuum and both H-beta emission line fades. So just to close, eROSITA has been detecting all these transient events, and we are carrying out approximately real-time multi-wavelength follow-ups of these events. And these demonstrate a large range of broad range of accretion flow categories with different kinds of H-beta and H-alpha profiles and responses. And these can serve as potential test beds for multiple extreme accretion models like disk instabilities or TDEs. So I end up. Thank you very much.
Okay, thank you very much. I think we have to move on in the interest of time. However, I just wanted to emphasize that it's something what we would like to have to do with radio. Also with X-rays in our system, it would be great to have access to some archives. And I've seen you've shown in your light curves so many nice X-ray light curves from multiple sources. So that would be very interesting to find out how to get to this data, and if this data is public, of course.
Yeah. Thank you.
We will get in touch for sure.
Yeah.
Thank you very much.
Thank you.
Okay, I'll take over the screen. And the last but not least, there is yet one more talk today. Hope you can survive this. I still have to find it. Okay. Right. Put the camera on our speaker here. Przemek Mikolajczyk.
To działa?
Działa. Powinien tylko użyć nawet. Okay. The cinema is yours.
Hi everybody. So for the last talk, very short, I know everybody wants to go to get some coffee probably. So I would like to introduce you to first results that we got from observations of from the all sky cameras. So this would be the state of the night sky at Polish astronomical observatories. And the author of this presentation is Dr. Sylwester Kołomański from University of Wrocław, and I will be presenting in his name. So here you have an example of two locations, two astronomical observatories separated by 50 kilometers. And in the left panel, you can see the 60 seconds exposure of the night sky at Białków Observatory. And in the right side, this picture is from Wrocław. As you can see, there is a 6 times difference in exposure time. And Wrocław is also visible in this picture in the left, creating this light island in the south. But you can also take this picture in the right using the same exposure time as the one in the left. Of course, light pollution, as every astronomer knows, will cause decrease in utility and value of instruments and will degrade observing conditions. And when we actually we'll try to show you what the sky in Wrocław actually looks like when you take the same exposure. It looks like this. So this is a true nature of the night sky in a 500,000 citizen city where our observatory is placed. So what we try to do with the project is to build all sky cameras using the available equipment, but also we put inside a digital photometer and other instruments which provide us with the environmental conditions like temperature, pressure, humidity, and so on and so on. So basically it's a weather station along with a photometer and all sky camera. And what we plan to do is to equip all the existing astronomical observatories in Poland, as well as all those abroad who are interested, with such equipment. So far we built 6 stations in 6 astronomical observatories. We have 2 more under construction. 2 more are now in signing, so we are signing contracts, and 7 more are planned. And by the end of next year, we should have around 15 stations, not 6. Okay, so what we do, we just put a very cheap cameras, RGB cameras, SMOS cameras, along with a professional lens. What we aim to do differently than the all sky cameras that you can buy in shop is to provide everybody with a high quality lens, not a lens which costs you $100, but the one that costs you $1,000 or close to it, because we really want to have a good quality of photometry from the sky. So these are the equipment list. And for you to understand what we try to show in measurements is just to know that there are 2 different units that you can measure the sky brightness in. The first one is NSU, and it stands for Natural Sky Unit, and it corresponds to this 21.4 to 21.9 magnitude per square arc second. So this is the unit that you measure the sky brightness in. It was based on data from Mexico, and it varies because of the sun activity variations over time. Okay, so here you can see I will show you some examples of the results. And here is one of our stations in Sopotnia Wielka. This is actually a community observatory, and it is the only place in Poland that is in a way protected against light pollution. And in the left side of this picture, and in the right you have the difference between lighting of the whole village when the whole village is the lighting is on and the lighting is off. So these are the darkest skies we have in any observatory in Poland, actually. So what they did, they kind of signed the contract with government that they will turn off the lights for 3.5 hours each night. Here's the difference between two observatories. In the right side you have Białków Observatory, which I showed you already, and on the left side you have Ostrowik Observatory, which is close to Warszawa. So this is basically one. These are similar places because the straight line distance between the city center and the observatory is quite the same. It's about 40-50 kilometers. But you can actually see twice the increase in the brightness of the sky, probably because Warsaw is such a huge city right now. We also capture auroras. So I think so far we did it 3 times, and twice the weather was good enough for us to actually take these pictures. So we also plan to build 2 of the stations this year and the next year, the second one on the seashore of Poland. So we could capture auroras even if they are quite dim. And some example exposures from the beginning of our project. We can capture satellites, we capture some meteors if they're bright enough, and so on. Sometimes we can see the halo around the sun or around the moon if it's at night. Of course, Noctilus and clouds as well are visible from time to time. And here, let's go to the first results. In the top panel, you can see something that's called scotogram, this is basically a histogram of how bright the nights are over the year. And here you can see at Ostrowik Observatory, there are 2 modes of this histogram. The first one corresponds to dark nights, and the one marked with number 2 corresponds to bright nights. So there are a lot of bright nights, even if the moon is not visible. Basically, due to the closeness of Warsaw. But when you go to, this is the example of a dark night. This is an example of a bright night. But when you go to Białków, the number 2 disappears. So even though the weather on average is the same, the amount of artificial light is substantially lower. So you cannot see the first mode. So anyhow, the natural sky unit is still, let's say, 60% to 80% higher than the real natural sky. Here you can also see the very bad nights. In the left, they renovated the observatory and decided to put the lights there, which there weren't before. So if there is a lot of dust in the atmosphere and there are clouds in the sky, you can see that there is spark lighting will give you a light bulb in the sky, and it's actually very well visible. These are 30 seconds exposure, so they're quite long, but anyway, it is visible by the naked eye on site. And here in the right panel, you can see the difference between lighting off and lighting on. So it's also visible. Yeah, so this is the comparison between these 2 observatories and other 2, which we have enough data to analyze. As you can see, Ostrowik is the worst because it's also sometimes it's 6 times more than natural sky, and Sopotnia is the best because it's only 30% or 50% more than natural sky. And what we are trying to do now, we are actually doing the photometry of the whole images. We can do the photometry of any region that we wish to track the changes over time. So the black line is the photometer, and the 3 other lines correspond to the color. And you can see that this goes with the same trend. But if we have this, we can also track the color changes. So this is what it looks like when there's cloudless light, or cloudless dawn or dusk. It's dominated, of course, by the short wavelengths because of the changing of the color of the sky. The same we can do during the night. The same we can do during the bad weather, and track the changes in the colors over time. That's what we did for Białków and for Wrocław, and we can clearly see that in this color plot there's a huge difference between these two observatories. So the trends are clearly visible. They have different angles for Białków and for Wrocław. Wrocław is much bluer because of the street lighting probably. And this plot may indicate directly the locations, light pollution and its sources. And so we did the analysis also for the aurora, and the aurora is also visible in the color plot, here marked with this dashed circle. And when you zoom in on this plot of the night, you will also see that it was captured. It was captured much better by the red color, yes, because of the oxygen emission at about 630 nanometers. So it is a very cheap, quite cheap camera, RGB with small sensor, and you can still very well detect things like that. What we plan to do next, we will divide the whole sky into, let's say, 100 sectors, and we'll track over the course of the years how the average flux will change in the sectors. It will clearly indicate when the lights will appear, when some other new light pollution will appear, and then we can take actions with the government to try to reduce it. So yeah, we have a full information about the bands. We have full information about the photometer. We also tested, I guess, close to 1,000 LEDs in the laboratory to be sure what are the proper characteristics of the emissions of these LEDs, then to detect which LEDs we can change or remove, and so on and so on. So it's quite ambitious project, but maybe I can update you on the next workshop on our work. So please visit our webpage if you are interested in the project. We have time lapses on YouTube. We have some Facebook and Instagram page. And if you want to contact us, ask any questions, please do. Thank you very much.
Thank you, Przemek. Your questions, comments? No.
Can you show back for the aurora when you said that this one?
Yes.
What? Yeah, no, the previous one. Or the next. Yeah. What was in the middle?
Clouds.
Ah, okay.
They're stronger than the aurora, right?
For sure.
I have another one, but if
Paolo?
Yes, I want to ask if there are some laws against those light pollution, because we had the same problem in Italy.
Yeah,
but they are not respected.
There are no laws in Europe. There is not a single country where there is a protection against light pollution. I think there are in
Italy,
in observatories maybe yes, but to be honest, I don't think anybody does care about that.
This is the problem.
Yeah, we want to quantify how much the light pollution increases, because nobody ever did that. Photometer is not enough, because photometer will give you a flux information and the color information, location information, and the position on the ground, right? Monica.
Russia, Spanish, France, Norway are getting new laws about light pollution, but it's really new, so we don't know what will happen.
Okay, Monica is saying that Russia, Norway, Italy, Spain, sorry, Russia, yes, Russia will probably keep up to the law. So yeah, there are maybe some laws, but I heard that it's much too late to change anything in Europe. So these laws have to be implemented in places like Chile, South Africa, Australia, and Russia, apparently, which we can still protect. But in in continental Europe, it's not possible. In Belgium or in Netherlands, you cannot see the Milky Way at all, and from anywhere.
In Italy, we have one region, Lazio, where
Yeah.
is Rome, where there is the astronomical observatory of Campo Catino,
Yeah.
and the astronomers of this observatory are fighting with good results against the light pollution.
Yeah, we would like to fight with good results as well. So we have some positive feedback, but I guess it's have to be joint action by governments, universities, scientists, and probably local communities as well.
Yes.
Yeah. Yes, Ilse.
There is even a part of the ORP project that is focusing on this.
Oh, so maybe we can get some money.
There is money allocated.
Ah, okay, okay. So yeah, we did it. Yeah, so, any more questions?
How many unis you can produce per month? I mean, how long it will take for have our entire network equipped with ALPS? How much money and how long time?
Okay, so single station is right now it's about $2,400, and it not only gives you the station, it gives you the web service, all the updates, upgrades, and so on, so on. So this is the money side. And on the time side, it takes much less time to produce 10 stations. It would take much less time to produce 10 stations than to do one a year, because we have to start the whole process again. So right now we will have to do 4. So it will probably take us somewhere in the vicinity of 2 weeks per station, maximum. We have the software is tested and ready, and the hardware we also know very well. So copying this is not complicated at all.
So I'm sure after this workshop, many of our observers will be contacting you.
Yeah, we already had some conversation. I don't remember, but I think Stefan was Basa was contacting us. So, and we also had the request for 4 stations for Hungary and 4 for Ukraine, right before the war. But we didn't take it because of the no time on our side. So if anybody is willing to help and have some technical skills in terms of programming, in terms of dealing with hardware and electronics, then please, we will welcome any help at all.
Well, I can see these could be connected to BHTOM, where we have the telescopes in our network, so that then we can even connect.
We can show the sky at the place, actually. It is very easy.
Even further than this.
Yeah.
If there is an observing request and the telescope is robotized, then the ALPS can tell us it's the time to open.
Yeah,
right?
yeah. I was also, I should have said that, but if you have your telescope like Michał does, with all-sky camera, there is no photometer there. But still, right now we know how to use the RGB images, how to calculate the fluxes and so on, to do it properly. And by entering very small changes in your software, we can download these images and process them for you. So over time, you will know how much the sky degrades and so on. So this is for free. We don't have to do basically anything. So if any of you have such a all-sky camera, please also let us know. We can display it in our webpage and process data for you and inform you after 2 years. Maybe you should turn off this light. You should contact these people and so on and so on. So please do.
Okay.
And Michał is.
I suggest we stop it here, Michał. Sorry, because the coffee is there. So we can continue on the coffee break, and there is no session after the coffee break. So there's only dinner left today. Upstairs on the 7th floor.
Yeah.
We can go for a swim in the swimming pool before the dinner. So you're most welcome. If you're not staying in this hotel, they will not kick you out. You can stay around. You can swim in the swimming pool. And the dinner is served at the invitation is for it's 7 for 7:30, as they used to say in the UK, right? So you can come from 7 until 7:30. The food will be served.
You also said you're gonna put order.
Oh yes. So in case you've forgotten what you've put on the form, I will put the PDF with all the list of people the results of the form on the Slack channel. So you will be asked by the waiter, what have you ordered? So you better check on Slack, okay? Otherwise you'll get vegetarian, okay? It will be on the roof, next to the swimming pool. So bring your swimming suit. Okay, thank you. And let's have coffee. Yes.
Dzięki za okazję.
Wait. I will now stop the Zoom, so thank you all.
Yeah, thanks, Lukasz. See you next time.